Hello everyone, welcome to Testpad MBA Prep. So in this session, we will cover each and every concept that is related to geometry. Geometry, I mean mensuration too. So we will make sure that each and every concept that's been tested ever in the previous CAT, previous ZAT and all the non-CAT exams, including CAT and non-CAT, all the exams. We'll make sure that each and every topic is covered, and we will also practice a lot of questions. So I will just explain you what are the topics that are covered in a brief way. We'll start with the lines and angles, and then we'll move on to the triangles. We'll discuss all the properties, all the types of triangles, everything, each and every theorem, and then we'll move on to the polygons. There we will look into the types of polygons, the theorems, the properties of all the polygons, and then we will move on to the quadrilaterals, where we will discuss all the quadrilaterals, the rectangle, the square, the each and every quadrilateral, the theorems, the properties of the quadrilaterals, and then we'll move on to the circles, and then we'll start mensuration and finish the wrap up this session. So it is critically important to cover, to have an idea on each of the topics. It's not like that you have idea on triangles and circulations and circles and you just skip the other parts. No, you have to have an idea on all the areas, all the topics, each and every theorem that is being discussed in this session. So don't skip this video. If you are already comfortable with geometry, then this will definitely act as a great revision session. Even if you start geometry from this video, right, for all the aspirants who haven't yet started studying geometry, you can start your preparation from this video. And let me tell you a misconception regarding CAT, especially whatever that are being tested in CAT as far as geometry is concerned. The misconception generally CAT tests tougher questions in geometry, from geometry. That is a great myth. That is a misconception. See, if you are clear about the theorems, the properties of all the topics of geometry and mensuration, then you can solve any question easily. The question might be somewhat tricky, but that is not so difficult. If you go through the past papers, right, past CAT papers, you will definitely come to know about that. There may be one or two questions in 2 to 3 years that may be very difficult, but generally the geometry questions are conceptual based. Most the conceptual based. After learning concepts, you have to know how to apply each and every theorem. That is what we will look into, we will practice in this whole session. And don't compare the mock questions, right, the questions that you face in your mock tests with the actual CAT. Don't compare. Definitely the CAT has got a different standard that is relatively easy when compared to the questions that you face in your mock tests. Don't panic even if you score less marks in your mock tests. If you want to actually practice the questions, you have to refer the. So let us start with lines and angles. So before starting, if you haven't subscribed our channel, do subscribe it, and you can also join our Telegram group, for which I have mentioned the link in the description. So let us start this session now. Let us quickly look into some basic concepts. The first one is point. What is a point? It's a location in space. It doesn't have any length nor breadth. And what is a line segment? A line segment is a straight line that has two endpoints. So this is my line segment. It has two endpoints. And what is a straight line? So a straight path in which we can extend in both the ways infinitely. So this is my line. This is my line segment. This is my point. And what is a ray? This is a straight line that has one end point, and the other end we can stretch it infinitely. And what is a plane? A plane is a flat surface, right? So let us take a plane. So a flat surface in which we can extend this infinitely in 2 dimensions. So these are the very basic concepts that everyone must be very clear. And let us look into some angles and types of angles. So yes, all these are basic concepts. I'm just explaining you very briefly. So angles and types of angles. So what is an angle? So if we have two rays here, this is ray 1 and this is ray 2, right? And this is point A. So this is an angle in which it consists of two rays, right, with a common point A. This common point is known as vertex, and this is the angle, and these two rays are also known as two sides of the angle, right? So when two rays or two line segments intersect, an angle is formed at the point of intersection, and that point is also known as the vertex or the initial point. And what are the types of angles? We have acute angle, we have right angle, we have obtuse angle, still we have straight angle, and also we have reflex angle. And what is the measure of acute angle? Acute angle, the value of this angle theta should be less than 90 degrees. Any angle which is less than 90 degrees is regarded as an acute angle, and right angle we know theta must be equal to 90 degrees. At obtuse angle, theta must be less than 180 degrees and this must be greater than 90 degrees, right? And straight angle, theta must be exactly equal to 180 degrees, and reflex angle, theta must be less than 360 degrees and it must be greater than 180 degrees, right? So we can represent the acute angle as like this, because this angle is less than 90 degrees. This is right angle exactly equal to 90 degrees. This is obtuse angle. This angle will be greater than 90 and less than 180. And this is a straight angle which is equal to 180 degrees, and this is reflex angle which is more than 180, less than 360 degrees. And what are supplementary and complementary angles? Supplementary means any two angles, right? Any two angles when they sum up to 180 degrees. For instance, we have, this is one angle which is, let's say, 45 degrees, and this is one more angle. This is acute angle, this is obtuse angle, which this is 135 degrees. And if we sum up 45 plus 135, this will be equal to 180 degrees. So exactly 180 degrees. So this is known as supplementary angle. What is complementary angle? When two angles sum up to 90 degrees, exactly 90 degrees, that is known as, those are known as complementary angles. Let us say this is 30 degrees, right? And this is 60 degrees. So when we add these two angles, let's say this is angle A and this is angle B. So when angle A plus angle B, this is equal to 90 degrees, exactly equal to 90 degrees. So these two form a complementary angle. So remember, the complementary means sum will be 90, exactly 90, and supplementary means sum will be exactly 180 degrees of any two angles. Linear pair. Let us take a straight line, right? So this is a straight line, and let us take an intersecting line here. Yes, and we know that a straight line makes 180 degrees. Here, this angle, if we say this angle to be 45 degrees, right? This angle to be 45 degrees. This angle must be equal to 135 degrees, because the total sum must be equal to 180 degrees, as this is a straight line. Hence, these two make a linear pair. But please remember, if we say this one to be 135 degrees and this one to be 45 degrees, right? 45 degrees. Even if we sum up these two will be equal to 180 degrees. However, these two won't be linear pair. Even though they sum up to 180 degrees, these two won't be a linear pair because they are not linear. One angle is here and one angle is here. They are not linear, even though these two belong to same geometric shape, same geometric figure. Unless they are linear, we cannot say that those two angles form a linear pair. Vertically opposite angles. Let us take a line, a straight line, and also let us take an intersecting line. Alright. So if I say this angle to be 45 degrees, what does this mean? How can you derive other angles? How can you find out the values of other angles? This is 45 degrees. As this angle is opposite to this angle, these are opposite, vertically opposite angles. So this angle is also 45 degrees, because vertically opposite angles are always equal. right? And one more thing, this is 45 degrees, and we learnt in the previous slide that the other angle, this angle will form a linear pair, right? These two must be 180 degrees. So if this is 45, this must be 135 degrees, because these two must sum up to 180 degrees. And if this is 135, this is the opposite angle of 135, so this must also be 135. So the total angle will be 360 degrees. These two are vertically opposite, these two are also vertically opposite, and this one form a linear pair. This angle also form a linear pair. So anyway, we can derive this. If we know at least the value of one angle, we can know the value of all the remaining three angles, right? Parallel lines and transversal. If we take two parallel lines, this is line 1 and this is line 2, and we also take a transversal here. This is a transversal. Transversal is something that cuts two parallel lines that intersect at two points, two distinct points. Now I am giving this value as 40 degrees. Okay, this value as 40 degrees. Let's assume this to be 40 degrees. Then my question to you is, find remaining angles. Find this angle, find this angle, find this, everything. Find all the angles. I am giving only the one value. How can you calculate? See, this is 40 degrees, right? This is 40 degrees. The point that you must remember is corresponding angles are equal. Corresponding angles are always equal. Corresponding angles are always equal. What is the corresponding angle to this 40 degrees? This one is the corresponding angle to this 40 degrees. So this one will be equal to this one. This angle will be equal to this angle because they are corresponding angles. And there is one more thing to remember, which is interior opposite angles must be supplementary. Interior opposite angles are always supplementary. Supplementary in the sense the two angles must be equal to, their sum must be equal to 180 degrees, exactly 180 degrees. So what are the interior opposite angles here in this figure? Interior opposite angles, let us take 40. What is the interior opposite angle to this 40 degrees? Okay, let us take one more angle. So this is 40 and this is also 40 because these two are vertical opposite angles. So this 40 is interior angle now. This is exterior angle, this is interior angle. What is my interior opposite angle for this 40 degrees? This is my opposite angle. So these two must sum up to 180 degrees. Already this is 40. So this will be equal to 140 degrees. This angle will be 140 degrees and this is 40 degrees. If this is 140 degrees, this is vertically opposite and this is also 140, and this is 40 degrees. So this is vertically opposite, this is 40 degrees. And if this is 40 degrees, these two must form this angle and this angle must form a linear pair. So if this is 40, this must be 140 degrees, and if this is 40, this must be 140 degrees, because these two form a linear pair, as well as 140 and 140, these two are vertically opposite angles. See, there are a lot of ways to calculate the values of angles. This is only one way. You can also say that alternate interior angles and alternate exterior angles are also equal. So in that way also you can find the values of the angles. However, the values do not change, but you must remember these rules. What are the rules? Alternate interior angles. Interior angles are equal. Alternate exterior angles are also equal always. Alright. So what are alternate interior angles? Let me erase this and make it clear so that I will explain you. See, this is my exterior angle. What are exterior angles? Which are outside this area, right? So this is my exterior angle, this is my one more exterior angle, this is one exterior angle, this is one exterior angle. What are interior angles? Which are within this space. So this is my interior angles. There are 4 interior angles and 4 exterior angles, right? Now this is one angle, let's say 45 degrees, right? 45 degrees. What is the alternate angle to this? This is the alternate angle, and this is 45 degrees. And what is the corresponding angle to this angle? This is corresponding angle, right? If this is the case, if this is 45, this must be 135, and if this is 135, the corresponding angle of this 135 is this one. So corresponding angles will always be like this. If this is the angle, this will be the corresponding angle, or if this is the angle, this will be corresponding to it. If this is the angle, this will be corresponding to it. If this is the angle, this will be corresponding to it. But alternate angles are not like that. So if this is 45, this is also 45, as these are opposite vertically opposite angles, and if this is 45, this will also be 45, as these are alternate interior angles, right? These are alternate exterior angles, these are alternate interior angles. If I say this one to be 135 degrees, then the alternate angle for this is this one, 135. So alternate angles go like this one and this one. These exterior angles, this one and this one, these two are exterior angles. This one and the alternate interior angles, and this one is a pair of alternate interior angles. So let us solve this. If the figure AB is parallel to CD, so AB is parallel to CD. Alright. If angle ABE, so this angle is 110 degrees, and angle BED, where is BED? This one is 25 degrees. Find the angle, measure of the angle CD. So this is the angle which we must find out. So what can be our approach? Just think about it. See, angle, these two sides are parallel, right? These two sides are parallel. So if we extend this side, right? If we extend this side, then you can be very much clear that this is 110 and this must also be 110 degrees. Why 110 degrees? These two are corresponding angles, right? These two are corresponding angles. And if this is 110, this is 25, and this is a triangle, right? We can say that all the interior angles of a triangle must sum up to 180 degrees. So 180 degrees minus 110 minus 25, so this will be equal to 45 degrees. So all the interior angles are now summing up to 180 degrees. And if this is 45, as this is a straight line, this is 45, this will definitely form a linear pair. This is already making 45 degrees, so this will be equal to 180 minus 45 degrees. This will be equal to 135 degrees. So angle CDE is equal to 135 degrees. See, just this is an application of the theoretical concepts that we have learnt till now. Let us solve this. AB is parallel to CD. AB is parallel to CD. Angle QPB. So this angle is equal to 105 degrees. And angle QRC. This is equal to 35 degrees. Find the measure of angle PQR. PQ and R. So this is what we must find out. Now, these two are parallel lines, right? These two are parallel lines. Parallel line segments. If I draw another line that is parallel to both AB and CD, right? If I draw this line, now this 105 and this, can you reflect any property, any rule, any property? So this is 105 degrees. So this must be equal to 75 degrees, because these two are interior opposite angles, right? 105 degrees is opposite to 75 degrees. This angle is opposite to this angle. So these two must sum up to 180 degrees, as these two must be supplementary. So if this is 75 degrees, right? These two, this 35 degrees and this angle, these two angles are alternate interior angles. So alternate interior angles are always equal. So this must also be 35 degrees. So we are asked to find out this angle. So 75 degrees plus 35 degrees. This will be equal to 110 degrees. So 110 degrees is the answer. See, we just applied the alternate angles concept plus alternate interior angles concept plus interior opposite angles. Interior opposite angles, as interior opposite angles are always supplementary, and alternate interior and alternate exterior angles are equal. This 105 and this 75 make 180 degrees, as these are interior opposite angles, and this 35 is equal to this 35 because these are alternate angles. So this 105 and this 35 this 75 are equal because these are interior opposite angles, and interior opposite angles make sum up to 180 degrees. They are always supplementary. And 35 and 35, these two are equal, as these are interior alternate angles. Now, properties of triangles. So let us look into the angle related properties of triangles. We know the sum of the three angles, the internal angles of a triangle, are the sum is 180 degrees, right? These are the three internal angles, and sum of three external angles, exterior angles, is equal to 360 degrees. The exterior angle is always equal to the sum of two interior opposite angles, right? Not just two interior angles that are opposite to each other. Now, how can this exterior angle be equal to 360 degrees? Interior angles are 180 degrees, but however, exterior angles are 360 degrees. Why is it so? Let us prove this so that you will be clear. No, CAT or any exam, any AB school entrance exam doesn't ask you to prove, doesn't test you to prove any theorem or anything. Just for your understanding, so that you will remember this in a much better way. Let us take a triangle here. Let us take a triangle. Let us name them A, B and C. So ABC and ABC are the vertices of the triangle. These are the internal angles, right? Angle A and angle B and angle C are internal angles. If we extend this line and this line and this one, we know this is a line and these two make a linear pair, right? These two make a linear pair, and these two make a linear pair, and these two make a linear pair, right? Now if we say this is angle A, this is angle C, this is angle A, and this is angle B, this is angle C, this angle will be equal to 180 minus angle C. This exterior angle will be equal to 180 degrees minus angle B, and this exterior angle will be equal to 180 degrees minus angle A, because these two must sum up to 180 degrees, as these form a linear pair, right? Let us mark the exterior angles as angle X, Y and Z. So angle X plus angle Y plus angle Z will be equal to these three. 180 minus angle C plus 180 degrees minus angle B plus 180 degrees minus angle A. So this will be equal to 3 into 180 degrees minus angle A plus angle B plus angle C. Now 3 into 180 degrees minus, we know angle A plus angle B plus angle C. These three interior angles will definitely sum up to 180 degrees. This is the basic property of a triangle. So this will be equal to 2 into 180 degrees, and this is equal to 360 degrees. What is this? Angle X plus angle Y plus angle Z, because these three are exterior angles. Hence, the exterior angles will definitely sum up to 360 degrees. See, we have two pairs of exterior angles actually. We can take, if we extend this line, we'll form a linear pair like this. However, if we do not extend this line, right, we have to extend this line, and now this will form a linear pair instead of this. In the same way, if we extend this line, we have to extend like this, and we have to extend like this. We shouldn't take all the cases at a time, right? So three exterior angles sum up to 360 degrees. Three interior angles sum up to 180 degrees. This is what you must remember. Properties of triangles, side related. Now, the sum of any two sides is greater than the third side, right? Sum of any two sides must be greater than third side. Let us say we have the three sides of a triangle as this is 10 centimeter, let's say this is 8 centimeter, and this is 2 centimeter. Can you form a triangle by using these three sides? Can you form a triangle? No, absolutely no, because the sum of any two sides must be greater than the third side. Greater. Here if we observe, take any two sides, 10 plus 2, 10 plus 2, and this side is 8. This is definitely less than the third side. This is greater than third side. However, if you consider these two sides, 8 plus 2, this is equal to 10. 10 and this side is also equal to 10. Now 10 is not greater than 10. Then 10 is equal to 10. That's the reason why you cannot form a triangle by using 10 centimeter, 2 centimeter, 8. 10, 2 and 8. However, you can make this even this is a little bit more than the third side. For instance, if we make this as 10.5, even it's 10.5, this is greater than 10, hence you can form a triangle. Like if we make it 2.5, then we can form a triangle by using these three sides. So what I want to explain you is, let us take S1, S2 and S3. These three are the sides of triangle. Now S1 plus S2, see S3 being the largest side. Okay, so S1 plus S2 must be greater than S3, which is the largest side, and there is no point in taking value in taking S1 plus S3 is equal to S2. Why? Because S3 is greater. S3 is the largest side. We know that if we sum up largest side to any other side, that will definitely be greater. So there is no point in taking largest side plus smaller side against the smaller side that is remained, right? Among the three sides S1, S2 and S3, you have to sum up two smaller sides against the larger side. If this is satisfied, if two smaller sides are greater than the larger side, then that will definitely be a triangle. The difference of any two sides is lesser than the third side. You can use this and you can just think about this. I will give you some sides, 8 centimeter, 3 centimeter, 10 centimeter. You can just use this and calculate the difference. You can just have the mental calculation and check whether this is valid or not. These all are valid. These all are properties of triangles. You can check them. Side opposite the greater angle is greater and vice versa. Side opposite to the greater angle. What does this mean? Let us say this is my triangle, right? This is my triangle. This is definitely obtuse angle, right? More than 90 degrees. This is obtuse angle. This is definitely less than this angle. Let us take A, B and C. So angle B is greater than angle A and angle C. Clear? Now, side opposite to the greatest angle is greater. This is the greatest angle, right? Greatest angle. Now, the side that is opposite is AC is opposite to this greatest angle. So AC must be the greatest side. So here angle B is greater than angle A. Hence, the side opposite to angle B, which is AB, will be greater than the side opposite to angle A, which is BC. Alright. Same applies with angle C as well. Angle B is greater than angle C, so the side opposite to angle B will definitely be greater than the side opposite to angle C, that is AB. Classification of triangles on the basis of angles. Now we can define these three angles according to as far as the classification is concerned. The first one is acute angle. Acute triangle is when all the angles are less than 90 degrees. Right? In a triangle, if each and every angle is less than 90 degrees, that is an acute angle. Right angle, exactly one angle is equal to 90 degrees. Obtuse angle, exactly one angle is an obtuse angle. right? Exactly one angle is obtuse angle. If this is obtuse angle, which is, let's say, 110 degrees, then these two must be definitely acute angles. And here is a question to you. Can you find out whether a triangle is acute if you know the dimensions of its sides? Now here is a question to you. How many minimum number of acute angles will be there in a triangle? Take any triangle. How many minimum number of angles can be there? Acute angles can be there. Minimum of 2 acute angles definitely be there. And the third angle will be either right angle or obtuse angle or acute. It can also be acute, but 2 angles definitely will be acute angles. The third one will either be right angle in this case, or obtuse angle in this case, or one more acute angle as in the first case, right? Now classification according to the sides, based on the sides. The first type is scalene triangle, where no two sides are of equal length. So all the angles, all the sides of the triangle are of different lengths, which means, let us say this is a triangle of A, B and C. These three are vertices, and the angle opposite to A is, the side opposite to angle A is A, and side opposite angle B is B, and side opposite angle C is C. Now A, B, C are sides. So according to the scalene triangle property, side A, the length of side A shouldn't be equal to length of side B, shouldn't be equal to length of side C. What about isosceles triangle? Exactly two sides are of equal length. Two sides are of equal length. If this is my isosceles triangle, A, B and C, A, B and C, side A shouldn't be equal to side C, but side C must be equal to side B. So these two are my isosceles triangle. And please remember, in isosceles triangle, as two sides are equal, two angles are also equal. They must be equal. We will look into the properties of isosceles triangles in the upcoming slides. So this is what you must remember. And whereas in equilateral triangle, all three sides are of equal length, same length, A, B, C. So side A will be equal to side B, will be equal to side C. Now let us solve this. The two sides of a triangle are 9 centimeters and 20 centimeters. If the magnitude of the third side is an odd number, what is the sum of all possible lengths of the third side? Try to solve this. Just pause the video and try to solve this. Okay, hope you tried. Here it is given that two sides of a triangle are 9 centimeters and 20 centimeters. Let us assume the third side to be S. Okay, this is the third side, and the first side is 9 centimeters, second side is 20 centimeters. S centimeter, S centimeter. Now there are two cases here. The first case is 20 centimeter is the greatest side of the triangle, right? Or S centimeters, the third side will be the greatest side of this triangle. We do not know the value of S, so we shall take two cases. This is case 1 and this is case 2. In case 1 we have the maximum value of the side as 20 centimeter, and in case 2 we have the maximum value of the side to be S centimeter. We also know that the sum of two angles, the sum of two sides of a triangle must be greater than third side. So sum of two sides, and I already mentioned in previous slides that while calculating the sum of any two sides of a triangle, calculate only the sum of two smaller sides against the larger side. Here what are the two smaller sides? If 20 is the largest side, S centimeters plus 9 centimeters is the smallest side. So these two sides must be greater than the other side. So S must be greater than 11. This is the first possibility that we got. And moving on to the other case, sum of two sides must be greater than third side. What are the two sides? If S is the greatest side, So S must be lesser than the other two sides, which are 9 plus 20 centimeters. So this will be equal to 29. So S must be less than 29. So we got two ranges here. S must be greater than 11 and less than 29. So what are the values that we can take? And here just remember the condition. Third side is an odd number. So we have got some limitations here. Third side is an odd number. S must be greater than 11. So after 11, what are the odd numbers? They are starting from 13, 15, 17 till 27, because S must be less than 29. So till 27. So how many numbers are there from 13 to 27? These are 8 numbers, 8 different values. But we are asked to find out the sum of all possible lengths of the third side. Sum of all possible lengths. These all are possible lengths. Just we need to find out the sum. So to find out the sum, we know the average is equal to sum by number. Average is equal to sum of all terms by number of terms. But we want only sum. So sum will be equal to average into number of values. So what is average? The first term plus last term by 2. So 13 plus 27 by 2 into what are the total number of units? 8. This will be equal to 160. So 160 is the sum of all the possible lengths of the third side. Hope you understood. Just go through this once. Let us solve this. How many non-congruent triangles can be formed with a perimeter of 9 units with each side having integer unit lengths? Okay. Now, the important word in this question is integer. In previous slide, the important word is odd number. In this question, the important word is integer unit lengths. Okay. How many non-congruent triangles? What is my congruency? Congruency means two triangles must be of same length, same dimensions, right? So that if I form two triangles of the same length, I can adjust the two triangles in such a way that one triangle will fit the other triangle. Let's say this is one triangle, this is my another triangle. These two dimensions are same. This is 5 units, this is 5 units, this is 5 units, this is 5 units, this is 3 units, this is 3 units. If I just twist this, if I just turn this, and if I turn this and if we put on this triangle, then it will adjust somehow, right? I can overlap this triangle, these two triangles on each other. So this is meant by congruency. But here we want non-congruent triangles. So different values, not same values, different values. So let us find out. So we know the perimeter of the triangle is 9. So all the sides must sum up to 9 units. 9 units. Let us assume C to be the maximum length. Now can you find out what is the maximum possible value that C can take? See, we can say that if C is the maximum length, then the two sides must be greater than the third side, which is C, right? So as C is the maximum side, the side having the maximum length, that must be lesser than the other two smaller sides, right? So A plus B will be greater than C, that is for sure. But what is the maximum value that C can take? If we let us add C on both sides again, A plus B plus C is greater than C plus C. Then what will happen? A plus B plus C, we know the value to be 9. So 9 will be greater than 2C and C will be less than 4.5, right? C will be less than 4.5. So what does this mean? The maximum value that C can take is 4.5, but here we have one condition, that is integer unit. We must only take the integer. So the maximum value that C can take is 4 units. This is the maximum value that C can take. So we found out this. Now let us calculate the possible lengths of C, B and A, all the three sides. If C is 4 units, then A and B must sum up to 5 units. So A can be 4 and 1, and don't tell me this 4 4 1 and 4 1 4, because these two are again congruent, because this is 4. If I take this 4 and this one to be 4, let us take this is 4, this is 4, and this is 1, and now this is A, B and C, and now you are taking this one as 1, this one as 4, and this one as 4. Somehow I can make this and overlap it, so these two will definitely be again congruent. So we have to take different values. If 4 4 1 is the case, then it shouldn't be repeated again. And if C is 4, we can also say that A to be 3 and B to be 2, and they sum up to 9. 4 3 and 2 9. Or else if C is 3, A can be 3 and B can also be 3. Is there any value? Is there any other value that satisfies this condition as well as this one? The two sides must be greater than the third side, as well as the sum of all the sides must be 9. There is no other condition. Hence, all the possible lengths, the possible cases are 3. So what is our question? How many non-congruent triangles can be formed? 3 non-congruent triangles can be formed. 3 triangles of different values, different dimensions can be formed. So this is the comprehensive process. We have a shortcut to find out the non-congruent triangles, the number of non-congruent triangles immediately. However, I am not the person who encourage to learn to make you learn the shortcuts. But in some non-CAT exams, right, like TISNET, SNAP, and MAT, where you are asked, you must improve your practice. So if any direct question comes like this, you can just improve. You can just put the formula and substitute. So for that purpose, I am just telling you the shortcut. See, the perimeter. If perimeter is even, right? If perimeter is even, then the number of triangles with integer sides can be calculated by the formula p square by 48, right? P square by 48. If perimeter is odd, like here 9 units, right? Perimeter is odd, then we can calculate the total triangles with by using the formula p plus 3 whole square by 48. Why I put the brackets here? Why I put the brackets? If these are integers, when we calculate it and if we get an integer, then that's not an issue. However, if we get any value in some points, in some decimal values, right, then we have to make it to the closest integer, right? We must make it to the closest integer. For instance, if we get the value as 4.2, then we must make it 4, or if we get 5.9, we must make it 6. So we have 9 units here. Let us apply this formula 9. So we have to take this case as 9 is odd. So 9 plus 3 whole square by 48. This will be equal to 12 square. 12 square is 144. 144 by 48. So this will be equal to 3. So here we got integer directly. So no need to change this. If any decimal form appears, then you must represent that to the closest integer. Now, if two sides of a triangle and an angle opposite to one of the two sides is given, can you find out the angle opposite to the other side? Just think about it. You have two sides of a triangle and an opposite angle, and an angle opposite to one of the two sides is given, and you are asked to find out the angle opposite to other side. Can you find? If yes, then what is the rule that you can apply? You can apply sine rule. For instance, we have A, B and C. These are three vertices of this triangle, and we have A, B, C. These are the sides of the triangle. A is equal to 10 centimeter, B is equal to 15 centimeter, right? Two sides are given, and an angle opposite to one of the two sides. Let us say the angle opposite to this side is 30 degrees. Okay, 30 degrees is given. Now find the angle B. Can you find? you can find by using sine rule. What is sine rule? Sine rule is a by sine A is equal to b by sine B is equal to c by sine C. This is equal to 2r. What is A, B and C? A, B and C are sides of triangle, lengths of sides. What is A, B and C? Capital A, capital B and capital C. These are the angles, value of angles. What is R? R is circumradius. Circumradius. It is represented by R. However, in this case, we are asked only the value of B, angle B. So you can ignore C and R. We do not know the value of R, right? Circumradius, nowhere it's given. So ignore this. Just calculate this. Calculate the value of B by using this. How can we calculate? What is A? A is 10 centimeter by, what is sine A? What is A? 30 degrees. So sine 30 degrees. This will be equal to, what is B? B is equal to 15 centimeter by sine B. That is what we must find. So substitute the values and calculate, you will get the value of B. But the sine formula remains the same, which is A by sine A is equal to B by sine B is equal to C by sine C is equal to 2R. And if you are asked to find out, if you are given all the three angles, right, all the three angles and all the three sides, and if you are asked to find the circumradius, right, circumradius, then you can substitute all the values and you can find circumradius also. So depending on the situation, you can make use of this sine rule. Now the next concept is, if three sides of a triangle are given, can you find the three angles of the triangle? Let us take A, B and C. Three sides are given. Side C, side B, side A. The values of A, B, C are also given. Just you are asked to find out what is angle A, what is angle B and what is angle C. Can you find out? Yes, you can. And what is the rule now? It's not sine rule, it is cosine rule. What is cosine rule? A square is equal to B square plus C square minus 2BC cos A. B square is equal to A square plus C square minus 2AC into cos B. Now C square is equal to A square plus B square minus 2AB into cos C. Small a, B, C are the sides of the triangle. Capital A, B, C are the angles of the triangle, right? So how can you find is, you know the values of A, B and C. Just substitute A, B, C, B, C, the values, and you will get cos A value, angle A value, right? In the same way, you can calculate for cos B and cos C as well. See, why I asked you the question first and I am revealing the rule next, because the question must enter into your mind first. If the rule enters into your mind, then you may be in a problem, because in exam, after looking at the question, this rule must come to your mind. Not the rule doesn't come to your mind before looking at the question. So you must face the question and you must remember the rule. Now, having said the importance of the sine rule and cosine rule, you must remember three important things, which are three important rules, let us say. The three are, let us take this triangle A, B and C. Side A, side B and side C. Okay. Now, if A is, let us name, so A is 10 centimeter, side A is 10 centimeter, side B is 6 centimeter and side C is 8 centimeter. If side A is 10 centimeter, then this is the greatest side among all, right? This is the greatest side, which means this angle opposite to this greatest side will be the greatest angle. So angle A must be the greatest angle of this triangle, right? If angle A is the greatest angle, no, we are just assuming angle A. You can take angle B or angle C as the greatest angles. That is your wish. Provided you must also change the values of the sides. If you take angle C as the greatest angle, then you have to make sure that the side which is opposite to angle C must be greatest. If you make angle B as greatest angle, you must make sure that the side opposite to angle B must be greatest. Okay, so in this case angle A is greatest angle. So if angle A is acute, which means angle A is less than 90 degrees. In this case, the side square A square will be less than B square plus C square. What is A square? The largest side square is less than the sum of the squares of the smallest sides. If angle A is right angle, right? If angle A is right angle, what does this mean? The largest side square will be equal to B square plus C square. This is the Pythagoras theorem, right? What if the angle A is obtuse angle? Obtuse angle. Now, in this case, A square, the largest square, will be greater than the other squares, B square plus C square. Just remember this. Now we can prove this, but proof is not necessary. Just remember these three. These three will definitely be handy while solving some problems. Okay, let us solve this. Consider obtuse angle triangles with sides 8 cm, 15 cm and x cm. If x is an integer, then how many such triangles exist? Now, there are two cases, like we discussed this similar problem in the previous slide. We don't know the value of x, so x can be the greatest side. Here 15 can also be the greatest side. So we have two cases, case 1 and case 2. What is case 1? The greatest side is x. In case 2, the greatest side is 15. Okay. So what are the values that x can take? Provided x is an integer, right? X is an integer. What are the values that x can take? We know the property of triangle, the sum of two sides must be greater than third side. Here, sum of two smaller sides must be greater than third side. So what are the smaller sides? If S is the greatest side, the smaller sides are 8 and 15. So 8 plus 15 must be greater than x. And so 23 must be greater than x. So x can be less than 23. X can take all the values that are less than 23. Now in the second case, the greatest side is 15. So the other two sides must be greater than, the sum must be greater than third side. What are the other sides? X plus 8, right? X plus 8 must be greater than 15. X plus 8. So x will be greater than 7. So x can take all the values that are greater than 7 and less than 23. We got the range here, right? We got the range. Now, in the question we are asked to find out the obtuse angle triangles. We are asked to consider obtuse angle triangles. And what is the condition for obtuse angle? Obtuse angle, so a square, the greatest side square will be greater than the sum of the smallest side squares. So what is the greatest side square in greatest side in the first case? X, right? So x square, this is for obtuse triangle. So x square must be greater than the other squares, 8 square plus 15 square. So x square will be greater than 289 and x will be greater than 17. This is the first case. And let us apply the obtuse angle property condition. So 15 square, the greatest side is 15. So 15 square will be greater than 8 square plus x square, and x square is less than 161. X must be less than 12. X is greater than 17 and x must be less than 23. 17 and 23, this is the range. So the values are 18, 19, 20, 21 till 22. So how many values? 1, 2, 3, 4, 5. So 5 values. 5 values. So in the second case, x must be greater than 7 and less than, see here, x square is less than 161, which means x is not exactly equal to 12. It is close to 13, because 12 square is 144, and so it is close to 13. So 12 point something, so it must be less than that value. So it can take up to 12. So here we have the values 8, 9, 10, 11 and 12. These are again 5 values. So here we got 5 values, and in case 2 also we got 5 values. So how many such triangles exist? Such triangles are 10 triangles. Centers of a triangle. How many centers are there? Centroid, orthocenter, circumcenter, incenter and excenter. We will look into one by one. So here first we shall look into centroid. So what is a centroid? A centroid is the meeting point of all the median, right? All the medians of triangles. So in a triangle we know there are maximum of 3 medians, but what is a median first? The median is a line that connects the midpoint of one side to the vertex of the opposite side. First, let us take a triangle now. So what are the midpoints of the sides? So midpoint of, so AB, AC and BC are my sides of this triangle. And what is the midpoint of AC? Midpoint of AC is D. And midpoint of AB is E. And midpoint of BC is F. So to form a centroid, as we know, centroid is the meeting point of the vertex and the opposite, the midpoint which is opposite of this vertex, and that midpoint is the midpoint of the opposite side. So here let us take B and D, right? Let us join B and D. So this is a median. So A is a vertex and F is the midpoint of the side opposite to A. This is one more median. C is the vertex and E is the midpoint of the opposite side of C, which is AB. So we got 3 medians here, right? And is there any intersecting point of these 3 medians? Yes, this is the intersecting point. This intersecting point is known as centroid. And remember this, the centroid may not be a perpendicular, right? It may not be perpendicular. In equilateral triangle, it can be it will be a perpendicular line, but in other cases, it won't be a perpendicular line. So this is the centroid, and some points to remember here are: this is my centroid. Centroid is denoted by G, right? It is denoted by G, and centroid divides any median in the ratio 1:2. So centroid divides the median in 1:2 ratio, where 1 is towards the side and 2 is towards the vertex. So this is my centroid. So this is dividing median BD in the ratio 2:1. So 2 is towards the vertex, which is B, and 1 is towards the side, which is AC. In the same way, the centroid G divides the median AF in the ratio 2:1, and it also divides the median CE in the ratio 2:1. And kindly observe here, ABC is my triangle. D is the midpoint of the side AC, and B is the vertex. So if I join BD, this is my median, right? And the next important point to remember is median divides the triangle into 2 equal parts, 2 equal areas. No matter how I change this, right, that will be equal. So if I make it an equilateral triangle, we can easily find out that this is divided into 2 equal halves. If we make it an acute angle, of course equilateral is also an acute angle triangle, again the median is dividing the triangle into 2 equal halves. So what can we infer? The median divides triangle into 2 equal areas. We can say that triangle BAD is equal to triangle BDC, right? Area of triangle BAD is equal to area of triangle BDC. Now another thing is, if we draw all the medians of a triangle, right? For that we have to first take the midpoint of BC, midpoint of AB, and then we have to join this. So vertex A and E, C and F. Now observe this, all 3 medians of this triangle are dividing this triangle into 6 triangles. This is triangle 1, this is triangle 2, this is triangle 3, this is triangle 4, this is 5, and this is 6. And this is the important thing, all these 6 triangles, 6 small triangles are of equal area, right? All are of equal area. Hence we can say that area of each small triangle, right? Area of each small triangle is equal to 1/6 of area of the big triangle, right? So this is the first center of a triangle, which is centroid. Now let us move on to orthocenter. So now you can observe this. No matter how I twist this triangle, all the medians, right? All the medians divide the triangle into 6 equal areas, 6 equal parts, so that all the areas of the 6 triangles are equal. Now it is 0.7. Each triangle is 0.7. Now it's 0.6. Now it's 0.7, 0.8, 0.3, 0.2, 0.1. So anyways, the triangle, the area of all the 6 triangles that are formed by the 3 medians of the triangle are equal. So the next center of a triangle is orthocenter, which is the intersecting point of all the altitudes of the triangle, right? So let us form a triangle first. So this is my triangle. But what is an altitude first? Altitude is a line from a vertex. We can draw it from a vertex of a triangle, and that line must be perpendicular to the opposite side of the vertex, right? For instance, this is a vertex, right? If we draw a line to the opposite side, this must make 90 degrees. This must be perpendicular at the point of intersection. So let us draw a perpendicular line from vertex B. So from vertex B, if I draw a line perpendicular to the opposite side, it is intersecting somewhere here and it is making 90 degrees. And from vertex A, we shall draw one more line which is perpendicular to BC. And from vertex C, we shall draw one more line which is perpendicular to AB. Let me adjust this triangle. Okay. So here we have altitudes B. So we have altitudes BD to the side AC, and BD is making 90 degrees. It is perpendicular at the point of intersection. And we have one more altitude AE and one more altitude is CF. So the meeting point of all these altitudes is known as orthocenter, and the point to remember here is the position of orthocenter. Position of orthocenter. So as this is an acute angle, right? Acute angle triangle, the orthocenter is inside the triangle. Just observe this. So see this. If we just observe the position of orthocenter, I'm just trying to make this triangle as right angle. So when I'm trying to make this triangle a right angle, the position of orthocenter is falling on the vertex that contains 90 degrees, right? So are you observing that? The vertex that contains 90 degrees. If I make it acute, the orthocenter is coming nicely inside the triangle. If I make the triangle obtuse, right? If I make the triangle obtuse, the orthocenter is outside the triangle. Why? Because this is an obtuse angle. This is greater than 90 degrees and the orthocenter is here. When it is right angle, it is falling on the vertex that contains 90 degrees. When it is acute, it is inside the triangle. So this is what you have to observe. So when the nature of the triangle is acute, the position of orthocenter is inside the triangle, right? Inside the triangle. When the triangle is right triangle, the orthocenter is on the vertex that contains right angle, on the vertex that has right angle. And if it is an obtuse triangle, then the orthocenter is outside the triangle. outside the triangle. Now, a small question to you. If I say this angle to be 40 degrees, right? This angle is 40 degrees. I want you to find out the value of this angle. Let us name this. So as this is a orthocenter, let us represent this with H. So angle B is equal to 40 degrees. What is angle H? How can you find out? Well, there are a lot of ways. First, I will explain you the traditional method, and then I will explain you the exact application of the orthocenter. So we know this is an altitude, right? This is an altitude, this is an altitude. So it is making 90 degrees at the point of intersection. So this is 90 degrees, this is 90 degrees. So this is again 90 degrees, this is also 90 degrees. Okay. So BFHE, right? BFHE. What is this? This is a quadrilateral, and sum of all the angles of a quadrilateral is 360 degrees. But we have 90 degrees. This is one more 90. We have 40 degrees. We are asked to find out this. So we have 90, 180 plus 220. We have 220. This is the remaining value. So 360 minus 220 is 140. So if this is 140, this must also be 140, as these are vertically opposite angles. So this is how you calculate the value of H, the value of angle H. But you can, whenever you find out, whenever you come across orthocenter and these types of questions, you can directly say that angle H is equal to, that is the angle that is formed at the orthocenter, is equal to 180 degrees minus angle A, right? 180 degrees minus angle A. So here angle H is equal to 180 degrees minus what is angle A? 40. So this is equal to 120 degrees. So you can directly substitute here, or else you can also follow this for better understanding. But this is what you have to remember. Angle which is formed at orthocenter will be equal to 180 minus angle of the vertex. And this is applied only in the case of orthocenter. There is a similar application in incenter, in the concept of incenter. Will explain you in this session. But this is the concept that is applicable only for orthocenter. For no other center of a triangle this is applicable. For only orthocenter this is applicable. So the next center of triangle is circumcenter, which is the intersecting point of all the perpendicular bisectors to all the sides. But what is meant by a bisector? There is a difference between a bisector and a perpendicular bisector. Let us assume any point on AC, on the side AC. Now if I select a line like this, right, which is passing through that point, this is also a bisector, but this is not a perpendicular bisector. So bisector is any line that passes through the midpoint of a side, right, that bisects exactly at the bisector is just a line that passes through the midpoint. If AC is the line that I have taken, let us assume that is passing through the midpoint of AC. Now this is a bisector, right? This is a bisector. This is just passing through the line. But what is a perpendicular bisector? Perpendicular bisector is something that passes through the midpoint as well as it makes 90 degrees at the point of intersection. So this is my perpendicular bisector of BA, and my perpendicular bisector of CB, and my perpendicular bisector of AC. See, have you observed? All these perpendicular bisectors are meeting at this point. So this is known as the circumcenter. Each and every perpendicular bisector is touching the midpoint of their sides, respective sides. First, let me mark them and let me adjust this triangle so that it will be much more clear to you. See, all the perpendicular bisectors need not pass through all the vertices, right? Need not pass through all the vertices. So here if you observe FG, JD and HI, these three are the perpendicular bisectors to the sides of the triangle, and these three intersect at B. This is known as circumcenter. So all the perpendicular bisectors intersect at one point, which is known as the circumcenter of the triangle. Now one more observation is that if we calculate the length from the circumcenter to any of the vertices, right? Let us calculate the length from this circumcenter to any of the vertices, right? From B to A, or from B to C, or from B to E, right? What can be the length? The length remains same. See, from B to C it is 5.4 units, from B to E it's again 5.4 units, from B to A this is again 5.4 units, because of which we are able to draw a circle, which is the circumcircle, right? So we can draw a circle by taking B as the circumcenter, right? So this is the circumcircle. As all the lengths are equal, the radius equal, right? From B to C, from B to A, from B to E, from the circumcenter to any of the vertices of the vertex of the triangle, the length is same. So that acts as the radius of the circumcircle. Here B acts as circumcenter as well as the center of the circle. Now if you observe, this triangle is an acute angle triangle. So the circumcenter is inside the triangle. What if this becomes a right angle triangle? Have you observed that? If it becomes a right angle triangle, the circumcenter is on the midpoint of the hypotenuse, right? If it is acute, it is inside the triangle. If it is right angle, it is on the midpoint of the hypotenuse. This is the hypotenuse. So it is, the circumcenter is exactly on the midpoint of the hypotenuse. If it is obtuse, so if the triangle is obtuse, the circumcenter is outside the triangle. So this is what you have to observe. Now the next concept is incenter. So incenter is the intersecting point of all the angular bisectors. But wait, what is meant by angular bisector? Angular bisector is any line that divides the angle into two equal halves, two equal parts. So what is the angular bisector of angle? What is the angular bisector of angle B? So this is my angular bisector of angle B, and my angular bisector of angle A is this, and obviously the angular bisector of angle C must meet at this point. So let us see whether it's meeting or not. Yes, it's meeting. So these are my angular bisectors. So this angular bisector is dividing angle B into two equal parts. Same applies to C and A as well. Alright. So if we observe, this is the incenter because this is the intersecting point of all the angular bisectors, right? All the angular bisectors. So this is the incenter, and this incenter is equidistant from all the sides, which means IB is equal to IC, IC is equal to IA. Alright. So because of this reason, I can draw a circle which has incenter as a center. So let us draw a circle now. See, this is the incircle that we are drawing now. So this is my incircle, and I is going to be my incenter. And what is in radius? In radius is the perpendicular distance of this incenter from each side. In radius, if we say this is Z, then IZ is my in radius, right? In radius. Now the next concept is excenter. It's not concept, but you shouldn't get stumbled when you hear this for the first time or when you hear it anywhere. So just I will brief you about this. So excenter is just a meeting point of the internal angular bisectors of one vertex and the external angular bisectors of two vertices. For instance, let us take this triangle. So this is my triangle. Now this is my angle. This is let us mark them as H, C and B. Alright. Now this is an angle, and the intersecting point. So let us draw the angular bisector. This is the angular bisector. So this is the internal angular bisector. If we extend this line further and this line further, this will be my exterior angle and this will be my one more exterior angle, right? So the angular bisector for this exterior angle will be like this, and the angular bisector for this exterior angle will be somewhere like this, right? So the angular bisector of one interior angle and two exterior angular bisectors meeting at this point. So this is my X center, right? So in the same way, you will get one X center here and one X center here. So in a triangle, you will get maximum of 3 X centers. So let us get back to this. So we learned that each median divides the triangle into two triangles of equal area, and centroid divides each median in the ratio 1:2. The one part will be towards the side and two parts will be towards the vertex, something like this. 2:1. Two parts will be towards vertex, which is A, and one part is towards the side, which is BC. And all the medians form 6 triangles of equal area, right? 6 triangles of equal area, and sum of squares of median is to sum of squares of sides is equal to 3:4, which means the ratio is 3:4. Let us say we have this is median 1, right? This is median 1, this is median 2, and this one is median 3, right? So according to this, median 1 square plus median 2 square plus median 3 square by sum of squares of sides. Let us take this one as A, this one as B, this one as C. So the squares of the sides are A square plus B square plus C square. This is equal to 3/4. So this is the relation that you must remember. Now, how can you find out the length of a median if the 3 sides of a triangle are given? We have a theorem to find this, but I want this to enter into your mind first. I don't want that theorem to enter into your mind first. So the moment you look at median in any question, then you must think of Apollonius theorem, right? So let us take a triangle. So this is my triangle with the vertices A, B and C. Let me draw a median. For median, we need a midpoint, right? So midpoint of B and C is somewhere here, and I am joining this vertex and this midpoint. So this is my median. So this theorem says that AB square, right? AB square plus AC square, this will be equal to 2 into AD square, which is the median, AD square plus any one of the two parts, either BD square or DC square, anything is fine. I am taking BD square now. You can take a DC square also, because midpoint divides two sides, median divides this side into two equal parts. So BD and DC both are of equal lengths. So anything you can take. So AB, I remember visually like this: AB square plus AC square is equal to 2 into AD square, which is median square, plus BD square or DC square, anything. So if you are given 3 sides of a triangle, which means you are given the value of AB, the value of AC, right? And also the value of BC, right? The value of BC. if the value of BC is given, let's say the value of BC is 10 units, right? Then what will be the value of BD? It will be 5 units, because the median divides exactly into two equal parts. So this is 5, this value is given, this value is given, this is given. You can find out the median, right? In this way you can apply this theorem. Orthocenter. So we learned, right, orthocenter is the exact intersecting point, the meeting point of all the altitudes. And we also learned that if this is a triangle and if this is my orthocenter H, right, this is my orthocenter. Let me join these two. Yes, if A is like 50 degrees, right? If A is 50 degrees, what is the angle H? Angle H is equal to how much? So you can simply say that angle H is 180 degrees minus angle A. This will be equal to 180 minus 50. This is the 130 degrees. Or you can also find like this. You can just extend these two lines. This is making 90 degrees. This is 90 degrees. So 90, 90, 50, which will be equal to 230, right? And the quadrilateral, the sum of all angles, internal angles of a quadrilateral is equal to 360. So 360 minus 230, this will be equal to 130. So this will be 130 degrees. So if this is 130, this will also be 130, as these are vertically opposite angles. This is one method. Or you can simply remember this 180 minus angle A. And we also learned, right, the position of orthocenter and nature of triangle. If the triangle is acute, right, if the triangle is acute, then the position of orthocenter is inside the triangle. If the triangle is right triangle, then the position of orthocenter is on the vertex, right, on the vertex containing the right triangle. And if the position is obtuse, if the nature of triangle is obtuse, then the position of the orthocenter is outside the triangle. Circumcenter, which is the meeting point of all the perpendicular bisectors to a side. Circumcenter, so circumradius is the concept that is that comes under circumcenter. Circumradius is the distance of the circumcenter from each vertex. We learned that circumcircle, the circle drawn with the circumcenter as the center, the radius as the circumradius. Okay. So position of circumcenter and the nature of triangle. So we learned that if the nature of triangle is acute, in acute angle triangle, the circumcenter is always inside the triangle, and if it is right angle triangle, it is on the midpoint. Circumcenter is on the midpoint of the hypotenuse, right, of the hypotenuse, somewhere like this, right? And if it is obtuse triangle, then it is outside the triangle. The circumcenter is outside the triangle. Now comes the incenter. Incenter is the meeting point of the angular bisectors. And the perpendicular distance of the incenter from each side is known as inradius. And what is incircle? Incircle is drawn within with the incenter as the center and inradius as the radius. Incenter as the center and inradius as the radius. If this is the incenter, and this is the incenter, this is the incircle, and the distance from the vertices from any of the vertex to the incenter is equal. Angle bisector theorem. What is this? What is the concept behind this? An angle bisector of a triangle divides the interior angles opposite side into two segments that are proportional to the other two sides of the triangle. Alright, let me take a triangle now. So this is my triangle. So this is A, this is B, and this is C. This is angle A, right? So let me draw an angular bisector. So this is angle bisector, and this is meeting at D. So according to this theorem, the angle bisector of a triangle divides the interior angles opposite side into two segments that are proportional to the other two sides of the triangle. So AB, right? AB by AC. These must be proportional to BD by DC. You can remember like this. AB by AC is equal to BD by DC. So these are proportional to the sides AB and AC. Let me give you a short example. So this is my in-center. We know when angular bisectors are there, then the concept of in-center appears, because the intersection point of all the angular bisectors is the in-center. So this is my in-center I, and this angle A is 40 degrees. Find angle I. For this, don't get confused with the orthocenter, right? This is that formula doesn't work here. You can calculate, I will derive it, but the formula you can apply directly is the measure of angle BIC, right? Angle BIC is equal to 90 degrees plus half of angle A, which means 90 degrees plus angle A is 40, so half of angle A is 20, so this is equal to 110 degrees. So angle I is equal to 110 degrees, as simple as that. But how did we know that BIC is equal to 90 degrees plus angle A by 2? See, for instance, let's say angle A, this entire is angle B, this is angle C. We know that angle A plus angle B plus angle C, this should be equal to 180 degrees. Now you are asked to find out this angle. So for this triangle, right? For this triangle. So you need not take the complete angle B. You need to take just this one, right? Just this one. And what is this? This is angular bisector, which means this divides the angle into two equal parts. So we can definitely say this is angle B by 2, that is half of angle B by 2. This is half of angle C by 2. Half of angle C. And this is half of angle A. So we can say that angle A by 2 plus angle B by 2 plus angle C by 2. So as we are dividing each and every angle with 2, right, we must also divide the RHS with 2. So 180 by 2, this is equal to 90. Now to make it 180, we shall add 90 degrees. Right, if we are adding 90 to the right hand side, we must also add to the left hand side, which means angle A by 2 plus 90 degrees. This must be equal to angle BIC. So this is just a derivation. You can, no need to remember this, but what you must remember is this one. Angle BIC is equal to 90 degrees plus half of angle A. So Euler's line. What is Euler's line? This is the line that connects 3 points. What are they? What are those? The centroid, the orthocenter and the circumcenter. These 3 points are connected by a line. This line is known as Euler's line. So one point here to notice, the centroid divides this line in the ratio 2:1. 2 is towards the orthocenter, 1 is towards the circumcenter. Simply like this. This is the orthocenter, this is the centroid, and this is circumcenter. So orthocenter is dividing in the ratio 2:1. 2 is towards orthocenter. So centroid is dividing in 2:1, 2 is towards orthocenter and 1 is towards circumcenter, right? And this Euler's rule is applicable to all triangles. There is no exception. However, we shall look into some special cases in which this is also applicable. But if we consider some special triangles like isosceles triangle where two sides are equal, right? So if you take an isosceles triangle ABC in which AB is equal to AC and B and C are also equal, the angles B and C are also equal. So the centroid of this isosceles triangle will somewhere be here. The incenter will lie here. the circumcenter will lie somewhere here, and the orthocenter will lie somewhere here, let's say. So if you observe these points, all the 4 points are collinear, right? So if we join all the 4, they are collinear. So this line is the median, this line is the altitude, this line is the perpendicular bisector, and this line is the angular bisector as well. So this is also Euler's rule. But the difference here is, we can say that the points are collinear from vertex A. However, we shouldn't say the same for from vertices B and C, right? Why? Because from B, let us say from B, my angular bisector may go like this. From C, my angular bisector may go like this. From B, my perpendicular bisector may go like this. From C, it may go like this, right? From B, my median may go like this. From C, my median may go like this. So from A, it is applicable. From A, all those will be on the straight line, single line, and all the points are collinear. But from B and C, it is not applicable, right? And this is the case of isosceles triangle. So what I am trying to say is, in an isosceles triangle, if you draw a line from the intersection point of the two equal sides, right, from here, right, from two equal sides, that line is the angular bisector, that line is the perpendicular bisector, right, that is the altitude, that is the median. And all the points in the sense, the centroid, incenter, circumcenter, orthocenter, all the 4 centers are collinear. But what about equilateral triangle? So let us take an equilateral triangle. Here, the incenter, the circumcenter, the centroid and orthocenter, they will be on the same point. And you can take any line. So if I, let's say A, B, C. So I'm joining B to D, C to F, and A to Y. Take any line, take AY, or be it BD, or be it FC. Let's take AY. So AY is my median, AY is my perpendicular bisector, angular bisector, altitude. It can also be BD. BD is also my median, BD is also my altitude, it's my angular bisector, and so on. So take any line that is your altitude, median, perpendicular bisector, and angular bisector, and this point is known as the centroid, circumcenter, orthocenter, and incenter. So this is about the equilateral triangle. And if you observe the ratio of, let's take the center as O. So OA and OY. OA is the circumradius, OY is the in radius, which is denoted by R, right? So OA is to OY is 2 by 1. The ratio of equilateral triangle divides circumradius and in radius. That is the midpoint, the orthocenter of the equilateral triangle. It can be orthocenter or any point, right? As this denotes all the points. So this point divides the circumradius as well as the in radius in the ratio 2:1. So whenever you see circumradius and in radius in the ratio 2:1, that means you have an equilateral triangle. Congruent triangles. So there is a difference between the congruent triangles and the similar triangles. So two triangles are congruent if the following two conditions are satisfied. The first one is the corresponding sides are of equal length. The corresponding internal angles are equal, right? So internal angles are equal and the sides are also of equal length. Let us say this is my triangle ABC, and C, right? This is one more triangle. This is R, P and Q, right? So RQ corresponding sides, which means RQ must be equal to AC, BC must be equal to PQ and RP must be equal to AB. And the second condition is the corresponding internal angles are also equal, such as angle R must be equal to angle A because those two are corresponding angles, and angle P must be equal to angle B, angle Q must be equal to angle C. If these two are satisfied, then these two are congruent triangles. The moment you know these two are congruent triangles, you can also infer that these two triangles can be overlapped exactly, right? So in simple words, congruent triangles are of same shape and same size. Congruency conditions. See here, there are 6 things that are equal, 3 angles and 3 sides, right? So this is one side, this is one side, this is one side. So 3 sides are involved and 3 angles are involved. But you need not verify all these things to conclude that we got 2 congruent triangles. We can just verify a few of them and we can right away conclude that they are congruent triangles. So how can we verify a few and conclude that whatever we got are congruent triangles? By using these congruency conditions. What are they? SSS, the side condition, which is all the 3 corresponding sides are of equal length. If we take 2 triangles, if we can prove that the corresponding sides are equal, right? If we say A, B, C, D, E and F, if we say that AB is equal to DE, BC is equal to EF and AC is equal to DF, then no need to prove that angles are equal. If corresponding 3 sides are equal, then angles will also be equal, right? Side, angle, side. A pair of corresponding sides and the included angle. See, this is important. Included angle are equal. Let us say corresponding sides, right? Okay. So A, B and C, D, E and F. Side, let us take AB. AB is equal to DE, right? These two are corresponding. Angle, the angle included. So let us take this. Angle A and angle D. So angle A is equal to angle D. And also if A, C and DF. So A, C is equal to DF. So if these 3 are satisfied, then we can say that these 2 are congruent triangles. No need to prove anything. Just if we are clear about these 3 things, then nothing else is to be proved. So this is a side, yes. This is angle A and this is side. Side, angle, side. This is included angle. ASA, angle, side, angle. So this is angle, this is side and this is angle. So this is angle, this is side and this is angle. So angle B must be equal to angle E and BC must be equal to EF and angle C is equal to angle F. If these 3 are satisfied, then we can say that the 2 triangles are congruent. AAS, angle, side. So a pair of corresponding angles and non-included side are equal. So let us take a pair of corresponding angles. Let us take, this is A, B, C, D, E and F. So angle A and angle D, if these 2 are equal, and angle B and angle E, these 2 are equal, and not included side. Okay, let us take, if we take AB and DE, then these 2 will be included side. Let us take BC and DF, or you can also take AC and DF, so that these 2 are not included. So if you can prove these 3 conditions, then you can say that these 2 are congruent triangles to each other. And the last one is HL, the hypotenuse leg of a right triangle condition, which means We know this is applicable for the right angle triangles, right? If we say this is A, B, C, D, E and F, two right triangles are congruent if the hypotenuse and one leg are equal. Let us say, as these two are hypotenuse, AC and DF, so AC must be equal to DF, so hypotenuse is equal, and one leg are also equal. So one leg, it can be AB is to DF, or BC can also be equal to EF. So let us look into the conditions in which the congruency doesn't exist. The two conditions are AAA, which is angle, angle, angle. It can also be known as AA condition in some sources. So this means all three corresponding internal angles are equal. For instance, this is my triangle ABC and this is my triangle DEF. This is 60, this is 60 degrees, this is 60 degrees, angle E is 60 degrees and angle F is also 60 degrees. So all the angles are satisfied. All three angles are satisfied. This doesn't mean these two are congruent. As you can see, these two are similar triangles. These two are not congruent, which means these two are not equal in length. So these two are not congruent triangles. The same applies with SSA, side-side angle, which means a pair of corresponding sides and the excluded internal angle are equal. For instance, if we take two triangles, then a pair of corresponding sides, let us take CA is equal to FD and CB is equal to FE, right? FE. These two are equal and excluded internal angle is also equal. So excluded internal angle, C is included, right? So let us take A and D. So angle A is also equal to angle D, but this doesn't mean these two are congruent, right? These two are just similar. You can say this. There is a lot of difference in the area of these two. This triangle is like this and this is quite narrow, right? But why I extended this triangle is the same size, the same length can be here or it can also be here. But how can you remember? AAA property is quite easy to remember because there is no much confusion and you can remember that this is not a condition of congruency. But what about SSA? The similar condition appeared here, which is AAS, right? So sometimes it will confuse you whether it's AAS or SSA, which doesn't come under congruency condition. So just remember like this. How I remember SSA is I read that from right to left, and we know there is no such congruency condition, that doesn't exist with this name, right? So how I remember SSA is I just read that from right to left, and we know there is no such congruency condition that exists with this name. Probably this is a good way to remember. So let us have a look into the properties of congruent triangles. So every corresponding parameters of two triangles are equal. Let us take two triangles. So these are my two triangles. So corresponding parameter, what does this mean? Corresponding parameters means there are two cases. The first one is side correspondence and the second one is angle correspondence. In side correspondence, each and every side will be equal. So AC, the corresponding side AC and PR will be equal. RQ and CB will be equal. AB and PQ are of equal length, and each and every line will be equal. Each and every length will be equal, which means if I draw a median, right, this is M1, and if I draw one more median, this is M2, M1 and M2 will also be equal. If I draw altitudes, altitude 1 and altitude 2 are also equal. Everything is equal as far as lengths are concerned. And if we consider angles, angle C is correspondent to angle R, so angle C and R are equal, angle A and angle P will be equal, and angle B and angle Q will be equal because these two are corresponding triangles, right? And if these two are corresponding triangles, all these must be equal. Similar triangles. So we understood what is meant by congruent triangle, what are meant by congruent triangles. Much more than congruent triangles, the concept of similar triangles is super important because it is easy to identify congruent triangles, but it takes a little bit of observation, good observation, to identify whether two triangles are similar or not. So two triangles are similar if the two conditions are satisfied, which are the two lengths of corresponding sides are proportional, not equal, proportional, and the two corresponding internal angles are equal. So sides must be proportional and internal angles must be equal. For instance, let us take two triangles, right? Two triangles. The corresponding sides are proportional. For instance, if we say CB is equal to 4, then RQ is equal to 40, AB is equal to 5, PQ is equal to 50, CA is equal to 3, and AP is equal to 30, which means AC by PR is equal to CB by QR. This is equal to AB by PQ. This is equal to 3 by 30, 4 by 40, 5 by 50. So this will be equal to 1 by 10. So corresponding sides are proportional. All the corresponding sides are proportional. And the corresponding internal angles are equal, which means angle C must be equal to angle R, angle A must be equal to angle P, angle B must be equal to angle Q. So if corresponding sides are proportional and corresponding internal angles are equal, then the triangles are similar to each other. So in simple words, these are of same shape and different size. And what are the properties of similar triangles? Every corresponding lengths of the two triangles are proportional. See, corresponding lengths are proportional means, let us take the median, or let us take the sides first. CB is proportional to RQ, right? This is equal to CA by side RP. This is equal to AB by PQ, right? So this is equal to 1 by 10. And the median is also a length, right? So the median M1 by M2 must also be 1:10. That must also be proportional. Not only sides are proportional, whatever the lengths are there, all the lengths are proportional. They must be proportional. That is the property of similar triangle. And what about the area? Of course, medians are proportional, altitudes are proportional, perpendicular bisectors are proportional in the same ratio 1 by 10 as the ratio of the sides. What about area? I want area of triangle ABC by area of triangle PQR. I want this. How can you find? We know area is half into base into height, right? So half into what is base? Base of ABC is AB, and height we do not know, so let us take it as altitude. So height is altitude, right? So altitude of AB by of triangle PQR. So half into what is base? Base is PQ into altitude of PQ. Altitude of PQ. So half and half get cancelled. We know AB by PQ ratio. What is that? AB by PQ 1 by 10. So this will be 1 and this will be 10. And we know altitude must also be in the ratio 1 by 10. So this will be 1 and this will be 10, which means 1 by 10 into 1 by 10, this is equal to 1 by 100. So this is equal to 1 by 10 whole square, which means area will be equal to the square of the length of the sides, right? In this case it is 1 by 10 whole square, the square of length of the corresponding sides. And this area part is very critical as far as the similar triangle property is concerned. Please remember this. We'll apply this in a question so that you will be very much clear about these properties. So ABCD is a trapezium with the two parallel sides 15 cm and 9 cm respectively. A line segment PQ parallel to the parallel sides is drawn such that P is on AB and Q is on CD, and PQ divides the trapezium into two figures of equal area. The length of the line segment PQ is, alright. So we have ABCD trapezium and 9 cm, AD is equal to 9 cm, BC is 15 centimeters, and AD is parallel to BC, and it is also given that PQ is parallel to the parallel sides. So P is on AB, so P must be here. So this is PQ, and PQ is parallel to BC, PQ is parallel to AD. So we are asked to find the length of line segment PQ. So this length must be found out. So let us extend this so that we can form a triangle. Alright, and let us mark this as M. The moment you see this, the moment you observe the parallel lines, you can say that this angle, this angle, this angle, these three are equal, since these three are corresponding angles, because these three are parallel, right? AD is parallel to PQ is parallel to BC. So angle A will be equal to angle P is also equal to angle B. Same goes here. Angle D is equal to angle Q is equal to angle C. These three are equal since they are corresponding angles. So MAD is my small triangle, MBC is my large triangle. If we want to find out area of smaller triangle by the area of larger triangle will be equal to, the last property we learnt that the area must be equal to, area of similar triangles must be equal to the square of the corresponding sides, right? So what is the corresponding sides here? AD and BC are corresponding sides. So 9 by 15 whole square. So we know that MAD and MBC, which is the smaller triangle and larger triangle, these three are corresponding, these three are similar triangles. When they are similar triangles, the area will be the square of the corresponding lengths. So 9 by 15 whole square, this is equal to 9 by 25. So the area of larger triangle is 25 units and area of smaller triangle is 9 units. So this is 9 units. So from 25 9 is deducted and the remaining is 16 units, right? So this triangle is of 9 units. The area of this triangle is 9 units and the remaining 16 units is for this trapezium, right? So 16 units, how can we divide 16 units? Here it is given that PQ divides the trapezium into two equal area, two figures of equal area, which means this area and this area is equal. So 16 will be divided into two equal areas. So 8 and 8, right? So what are we heading to? Where are we heading to? We found out the respective areas. We found out the smaller area. We have found out the area of trapezium and overall area. Everything we have. Now, if we find the area of smaller triangle by area of medium triangle, which is MAD is my smaller triangle, right? The area is 9. And medium triangle MPQ 9 plus 8 is 17, right? We know this must be the square of the corresponding sides. What are the corresponding sides? AD and PQ, AD by PQ whole square. But here we already know the value of AD is 9 centimeter, so just substitute 9 here and now use 9 by 17, this is equal to 9 square by PQ square, and this is equal to PQ square will be equal to 153, right? PQ square will be equal to 153, PQ is equal to root over 153. So the area, the length of the line segment PQ is equal to 153, root of 153 units. It's a very simple and beautiful question, just the application of the concept, the area of two similar triangles concept, right? So basic proportionality theorem. What does this say? If a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, the other two sides are divided in the same ratio. So if we take a triangle, right? If we take a triangle, let us name them as A, B, and C. And what is this? A line drawn parallel to one side of a triangle. Okay. This is a line drawn parallel to one side, which is BC, right? Let us name them as P and Q. So at two distinct points, the other two sides are divided in the same ratio. So these two sides are divided in the same ratio, which means AP by AB, AP by AB is equal to AQ by AC is equal to AQ by AC. It's not AP by PB, PB is equal to AQ by QC. No, not that, not like that. The other two sides are divided in the same ratio, right? So AP by AB is equal to AQ by AC. For instance, if AP is 9 units, then PB is equal to 27 units. If AQ is 10 units, then QC will be 30 units, which means 9 by 27 is equal to 10 by 30. This is equal to 1 by 3 is equal to 1 by 3. Hope you understood. Next comes the midpoint theorem, which is the segment joining two sides of a triangle at the midpoints of those sides is parallel to the third side and is half the length of the third side. So let us take a triangle again. So this is A, this is B, and this is C, right? The segment joining two sides of a triangle at the midpoints of those sides. Alright, so midpoints of those sides. Let us name the midpoint of AB here as M and the midpoint of AC is N. If we join these two lines, right, these two lines, this is parallel to the third side. So MN is parallel to BC, right, and is half the length of the third side, which means MN is equal to BC by 2. Alright. Now, properties of right triangles, really important, really important. As far as the MBA exams are concerned, it can be CAT, it can be XAT, or it can be any other non-CAT exams. And in geometry we can expect questions from triangles, from circles, right, and a combination of both triangles and circles. If there is a combination of a triangle and a circle, then there is a very high chance that there is an involvement of the right angle triangle. So right angle triangle, the properties, everything you must be very much clear, and you must be clear about their applications too. So properties of right angle triangles. The moment you hear or you look at a right angle, the first theorem that comes to your mind is Pythagoras theorem. So Pythagoras theorem that consists of three positive integers A, B, and C, such that let's first take a Pythagoras theorem. So A, B, and C, this is 90 degrees. You can say that AC square is equal to AB square plus BC square. The hypotenuse square is equal to the side square plus base square. And let us look into some Pythagorean triplets. See, Pythagorean triplets is somewhat necessary to remember at least some triplets, some primary and a few secondary triplets, so that your competitors will definitely remember these triplets. If you do not remember and if you try to calculate at that time, then you are literally wasting your time. So just remember the Pythagoras triplets. So some of the Pythagorean triplets are 3, 4, 5, right? 5, 12, 13, 7, 24, 25, 9, 40, 41, and 11, 60, 61. These are the primary triplets. These are primary triplets. So primary triplets are defined as the HCF of three numbers is 1. Let us take 3, 4, 5 or 5, 12, 13. The HCF of all these three numbers is 1. And the least number is odd. Here what is the least number? 3. 3 is odd. Here 5. 5 is odd. Here the least number is 7. Here 9. So the least number is odd and the HCF of all these three will be 1. Right? So these are the primary triplets. And secondary triplets are 8, 15, 17, 12, 35, 37, 20, 21, 29. At least you remember these. That must be enough, because these are frequently asked, very frequently asked. And secondary triplets can be derived from primary triplets. Let us see how. Secondary triplets can be directly derived from the primary triplets. Let us take 3, 4, 5 as primary triplets, right? If we multiply this with 2, what will we get? We get 6, 8, 10. This is also a triplet. And if we multiply with 100, it will be 300, 400 and 500. But why multiplication? Let us divide it with, let's say, 2. What will we get? We get 1.5, we get 2, 2.5. This is also a triplet. So by using primary triplets, we can form secondary triplets as well. But at least you must remember these primary triplets and these secondary triplets, right? So let us solve this. The square pyramid shown. Wait a moment, I will draw this. The square pyramid shown has altitude 6 and the side of the square base is equal to 8. What is the area of one of the triangular faces of the pyramid? So let me draw the pyramid. So this is the diagram which is given. So it is given that the altitude of the pyramid is 6, right? The altitude is 6. So this straight line, this altitude, this is 6 units, and the side of the square base is equal to 8. So this is 8 units, this is 8, this is 8, right? And the area of one of the triangular faces of the pyramid. See, if we extend this, right? If we extend this will be a right angle triangle, and this one will be the hypotenuse, and the hypotenuse is the square of this triangle ECD. That's a triangular face, and our hypotenuse will lie exactly on the triangular face ECD. See, why we are calculating like this? We extended this and to make a right angle triangle, because we know the base. Here we are asked to find the area of the triangular face. Area we know, half into base into height, right? Here base we know, that is 8, but height we do not know. How to calculate height? If we extend this and make a right angle triangle, this hypotenuse will be my height, right? The height of the triangular face, this triangular face. You can calculate for any triangular face. I am calculating for this triangular face. So the hypotenuse is my the height of the triangular face, which means if I calculate the hypotenuse, then I will get my height. So h square will be equal to, which means h square will be equal to, say I am considering this right angle triangle, this one, right, this one. So this is 6 units, this is, the base is 4 units, because the entire side is 8 units. As this is the altitude, it is meeting exactly at the center. This will be half of the side, so half of 8, this is 4. So 6 square plus 4 square, so h will be, hypotenuse will be equal to root 52, which is equal to 2 root 13. Hypotenuse is 2 root 13, which means my height is 2 root 13. So I can directly substitute here half into what is base. Base is 8. Base is 8. into 2 root 13, this will be equal to 8 root 13. 8 root 13 is one of the triangular faces area. So then the next theorem is altitude on hypotenuse. Let us take a right angle triangle. So this is my right angle triangle CAB. AB is my hypotenuse, and if we draw an altitude on the hypotenuse, right, this is my altitude, so it makes 90 degrees, right, it is perpendicular, this is 90 degrees. Let us mark this altitude as H, and the length of AC as B, and the length of CB as A, and the length of AB, right, the length of AB is C, this complete length, and the length of DB, the length of DB is R, and the length of AD is L, right. Here AB is my hypotenuse, and we have drawn the altitude on the hypotenuse. Here if you observe, so the theorem states that H square, which is my altitude square, right, H square is equal to L into R. L into R. H square is equal to L into R. A square is equal to R into C. A square is equal to R into C, and B square is equal to L into C. How I remember is, if you start with vertex B, right, then it will be A square is equal to R, right, everything must start from vertex B. A square is starting from vertex B, R is starting from vertex B, R, and again from vertex B till here, C square, C. So A square is equal to R into C. If you start from vertex A, it will be B square, which is starting from A, into L. So from A to L, from A to entirely. So A square is equal to B square is equal to L into C. A square is equal to R into C. We can prove this. We can prove the altitude on a hypotenuse theorem, but proof is not necessary. You can search some other sources, or you can just prove by yourself. But whenever a hypotenuse, a right angle triangle, and altitude are involved, you must remember this. Whenever a median is involved, you have to remember Apollonius theorem, right? Let us solve this. A semicircle is drawn with AB as its diameter. From C, a point on AB, a line perpendicular to AB is drawn, meeting the circumference of the semicircle at D. Given that AC is equal to 2 cm and CD is equal to 6 cm, the area of this semicircle will be. So this is a circle. We can ignore the second part. Just consider the first semicircle. Here the question talks about AB as the diameter. From C, a point on AB, right? A point on AB, a line perpendicular to AB is drawn, meeting the circumference of the semicircle at D. So from C, a perpendicular line to AB is drawn, meeting at D. So this is D and this is C. Alright. Given that AC is equal to 2 cm, AC is equal to 2 cm, CD is equal to 6 cm. So CD is equal to 6 cm. Alright. But we do not know the value of CB. Right. We do not know the value of CB. The area of the semicircle will be. Alright. So we are asked to find out the area of semicircle. In the previous slide, we learnt, right? So this is like the hypotenuse, altitude on hypotenuse, right, which means H square is equal to L into R. The same thing we can apply, but where is the right angle? Let us create the right angle. Let us join these two, right, and these two, right. So this will be a right angle. You will learn much more about this when we start the concept of circles. So this is right angle. Now H square is equal to L into R. The same thing apply here. 6 square is equal to 2 into something. We do not know that. Okay, that something is equal to 18 now. right? That is 18. So this is 18. So the diameter, what is the diameter? Diameter is 18 plus 2, 20 centimeter. Alright. So what is the area of semicircle? Area of semicircle is half pi r square. So half into pi into what is r? So diameter is 20, radius is 10. So 10 square. So this will be equal to half pi 100. So this is 50 pi. So the area of semicircle is 50 pi. See, all the questions that we are solving in this session are taken from previous year papers. It can be CAT, it can be SNAP, all the previous year papers, and these are most important questions. All are concept driven. So after understanding concepts, you must know how to apply them. The geometry is all about understanding the concepts, remembering the concepts, and the right concept must click in your mind at right time, right? Then you can attempt any question in geometry. It can be of any difficulty level. Now we shall deal with triangles, some special right angles, right? Some special right triangles. You are aware of that. You must be heard about the 90 60 30 triangle, or 90 45 45 triangle, right? Let me write it here. The 90 60 30 triangle and 90 45 45 triangle. So what is the side ratio? The side ratio of 90 60 30 triangle is 2 is to root 3 is to 1. I will explain this. Don't worry. The side ratio of 90 45 45 is root 2 is to 1 is to 1. So this is the side ratio. Okay. See, 90 60 30 triangle can be applied only if you have a triangle like this with 90 degrees, with 60 degrees and 30 degrees. For instance, if I say this, the opposite side of 90 degrees as 30. See, 90 60 30 2 is to 3 root 3 is to 1, which means the side opposite to 90 degrees and the side opposite to 60 degrees, the side opposite to 30 degrees must be in the ratio 2 is to root 3 is to root 1. In the same way, in 90 45 45 triangle, the side opposite to 90 degrees and the ratio of the side opposite to 90 degrees and the side opposite to 45 degrees and the side opposite to 45 degrees must be in the ratio root 2 is to 1 is to 1, right? So if I give you hypotenuse is 30 centimeter, let's say 30 centimeter. Now hypotenuse is opposite to 90 degrees, right? 90 degrees. From this what can we infer? You can infer that the other sides, the angle opposite to the side opposite to 60 degrees must be root 3 in terms of root 3, and the angle and the side opposite to root 30 is 1 if 30 centimeter is equal to 2, right? So if h is equal to 30, then the side opposite to 30 will be equal to 15 and the side opposite to 60 will be equal to 15 root 3. Alright. In the same way, if I have this 90 45 45 degrees, and the moment I say the hypotenuse is 10, this will be 10 by root 2 and this will also be 10 by root 2. Why 10 by root 2? See, 90 corresponds to root 2, right? 90 corresponds to root 2 and root 2 is 10 now. So if root 2 is 10, what is 1? So this will be, the question mark will be 10 by root 2. So this is 10 by 2 and this is 10 by root 2. Hope you understood how to apply this rule 90 60 30 and 90 45 45. Just remember these two ratios. That is more than enough. and wherever you find 90-60-30 triangle and 90-45-45 triangle, these two ratios must appear in your mind. Let us solve this. See, in the figure, AD is parallel to BC. So AD is parallel to BC. AB is equal to 8 units. So AB is equal to 8 units. AD is equal to 10 units. So this is equal to 10 units. AD is parallel to BC. Angle ABC, this is equal to 60 degrees, right? And it's also given that angle BCD is equal to 45 degrees. So AD is parallel to BC, which means from this point to this point it is 10 units. We can also say that from this point to this point this is also equal to 10 units, right? And this is 90 degrees, so this is also equal to 90 degrees. The moment you say 90-60, this will be 30. So this is 90, this is also 90, so this is 45. So 90-60-30 triangle, and here it is 90-45-45 triangle. The 8 is opposite to 90 degree. What is the ratio of 90-60-30? 2 is to root 3 is to 1. This is 90-60-30 triangle, right? 90-60-30 triangle. The side opposite to 90 degree is 8, right? Is 8, which means this will be equal to 4 root 3. 4. This will be equal to 4, and this is equal to 4 root 3, because this 4 is opposite to 30 degree and this 4 root 3 is opposite to 60 degree. And what about this? What about 90-45-45? 90-45-45. What is the ratio? The ratio is root 2 is to 1 is to 1. Now we can say that if this is 4 root 3, this will also be equal to 4 root 3, because these two are parallel, right? These two are parallel and equal. The side opposite to 45 degrees is 4 root 3, which means the side opposite to this 45 degrees must also be 4 root 3, and if this is 4 root 3, the side opposite to 90 degrees must be root 2 into 4 root 3, which is equal to 4 root 6. Now you can just add all this to get the perimeter of this quadrilateral. Just add them. It's 10 plus 10 plus 8. So this will be equal to 32 plus, this is 4 root 3 plus, and this is 4 root 3 and this is 4 root 6. So 4 root 6. So 32 plus 4 root 3 plus 4 root 6 is the perimeter of the quadrilateral ABCD. Properties of equilateral triangle. So in an equilateral triangle, all the interior angles are equal and all sides are equal. We know that. And any two equilateral triangles are similar triangles. Yes, they are similar. The sides are equal. The sides are proportional. The angles are equal, right? And from any side, median, angle bisector, perpendicular bisector, and altitudes are the same line. The centroid, incenter, circumcenter, orthocenter, all the centers are at the same point. Yes. For a given perimeter, equilateral triangle has the largest area. Now, this is the point that we haven't discussed, which is for given perimeter. For given perimeter, let's say we have scalene triangle. We have isosceles triangle. We have right triangle, and we have equilateral triangle, right? Here, what is the point here? For given perimeter, equilateral triangle has the largest area. If we say the area of the scalene triangle is, the perimeter of scalene triangle is 180 centimeter. The isosceles triangle perimeter is also 180 centimeter. The perimeter of the right angle triangle is also 180 centimeter, and the perimeter of equilateral triangle is also 180 centimeter. Now, given all the perimeters of the respective triangles is the same, right? Same. The equilateral triangle has got the maximum area. Equilateral has got the maximum area. Now, the inverse is also true. Which means if I say area of the scalene triangle is, let's say, 100 centimeters square, right? Area of isosceles triangle is also 100 centimeters square. Area of right angle triangle is also 100 centimeters square, and area of equilateral triangle is also 100 centimeters square. Now the perimeter will be minimum for equilateral triangle. When perimeter is equal for all the triangles, area is maximum. When area is equal for all the triangles, perimeter is minimum. Remember this. So let us take an equilateral triangle here. Equilateral triangle. So this is 60 degree, this is 60, this is 60. So this is my median, this is my angular bisector, this is my perpendicular bisector, everything. And this is the height, the altitude also. If this is 60, right, if this is 60, this will be 30 and this will be 30, because angular bisector divides the angle into two equal parts. And this is 90, we know that is intersecting at 90 degrees. Since we know the centroid, orthocenter and everything is at one point, that this point divides the line in 2:1 ratio, right? 2 is towards the vertex A, 1 is towards the side BC. Now, what is the area of triangle? Area of equilateral triangle. What is the area of equilateral triangle? If we say this is A, right? This is A units. This is A units. What is the area of equilateral triangle? It's half into base. What is base? Base is A into height. What is height? Let us name it as H. Now half into base into what is height of the equilateral triangle? See, this is 90 60 30 triangle, right? 90 60 30 triangle. So 90, or what is opposite to 90 degree? It is A. It is A. And since this is A, this will be A by 2 and this will also be A by 2, right? So angle opposite to 90 degrees is A, angle opposite to 30 degrees is A by 2, then angle opposite to, the side opposite to angle 30 degrees is A by 2, side opposite to 90 degrees is A. So side opposite to 60 degrees will be root 3A by 2. This is our height, root 3A by 2. So this will be equal to root 3A square by 4. This is the area of equilateral triangle. You can simply remember like this. However, if you want to derive, you can derive like this. And the second one is, what is circumradius? What is circumradius? Circumradius, we know circumradius is 2/3 of the height. So 2/3 of the height is A by root 3. In terms of height, it is 2 by 3 of H. In terms of altitude, it is A by root 3. And how did we get this A by root 3? I just substitute in the place of H, I just substituted. Now what about in radius? In radius is 1/3 of H, right? So in radius is always this one, right? Circumradius is always the above part. So in radius is 1, the complete part is 3, so 1/3 of H, 1/3 of height. So this is in terms of height, and in terms of altitude this is A by 2 root 3, A by 2 root 3. So these are the properties of the equilateral triangle. Now we shall look into the properties of isosceles triangle. In an isosceles triangle, as we know, exactly two sides and two angles are equal, right? Two sides and two angles are equal. So this is my isosceles triangle A, B and C, right? A, B and C. Now this is my median, this is my angular bisector, this is my altitude, this is my perpendicular bisector AD, right? This is my median, angular bisector, altitude, perpendicular bisector. And we can say that all the points lie on the same line. The orthocenter, circumcenter, right? The centroid, the incenter, all the four centers lie on the same line. And what is the area of isosceles triangle? Area of isosceles triangle is B into 4A square minus B square by 4. Often we don't often use this, but it is better to have an idea, because we can derive this, but in exam it is advised not to derive any formula. So better to remember this the area of isosceles triangle directly instead of deriving. So this is the area of isosceles triangle. Now we shall learn the area of triangles. What is the area of triangle? The basic formula is half into base into height. All right. What is Heron's formula? Heron's formula is root of s into s minus a into s minus b into s minus c, where s is my semi-perimeter, a plus b plus c by 2. All right. If we take a triangle, we take this triangle, right, a b and c. This is my height h, this is my base bc, and this is perpendicular 90 degrees. This is ac, this is b, this is a. All right. So this is my semi-perimeter. This is the Heron's formula. And one more formula to calculate area of triangle is AB sine theta by 2. This is when we have the one of the included angle. Please remember, sine theta, this theta is included angle, not the excluded angle. See, when you have a, when you have b, right, then sine theta becomes angle c, not angle b, not angle a. Theta becomes angle c because to this a and b, c is the only included angle, right? Please remember this. And in terms of circumradius, what is the area of triangle? The area of triangle is ABC. ABC are the sides of the triangle. ABC by 4R. R is the circumradius. R is the circumradius. In terms of in radius, area is equal to R into S. What is R? Small r. Small r is in radius, and S is my semi-perimeter, which is this one. You can calculate any area. You can calculate any area in any question by using these formulae. Nothing is required. Just learn this. Just have an idea on all this. Okay. Let us solve this. I think this appeared in CAT 2019 slot 2. Yes, this appeared in CAT 2019 slot 2. Okay. In a triangle ABC, medians AD and BE are perpendicular to each other and have lengths 12 centimeter and 9 centimeter respectively. Then the area of triangle is. Alright. Okay, let me draw the triangle. Of course, triangle is not given in the actual exam. Okay, this is my triangle A, B and C, and it's also given that medians AD. Okay, let me take the midpoint of BC. This is the midpoint. And this is my median from vertex A, and this is my median from vertex B. So let us name it as D, this one as E. Okay. Now 12 centimeter, 9 centimeter respectively. So AD is equal to 12 centimeter. AD is equal to 12 centimeter. AD is 12 centimeter means, remember, the median divides the the centroid divides the median in the ratio 2:1. 2 is towards the vertex, 1 is towards the base, to the side, right, to the side. As AD is 12 centimeter, right, divide that in this ratio 2:1. So this will be 8:4. In the same way, divide 9 in the ratio 2:1, right? So it will be 6:3. Now we are asked to find the area of triangle ABC. And in the beginning we learned that median divides the triangle into two equal parts of two equal areas. If we describe all the medians, then all the medians divide into 6 equal areas. But here, if we consider only one median, it divides into 2 equal areas. Now if we take this, ABD, so 2 into area of ABD is equal to area of, or 2 into area of ADC is also equal to area of ABC. That's fine. Now 2 into what is area of ABD? ABD. What is this area? Half into base. What is base? Base is AD, right? Base is AD. So we have AD as base and height as BG, right? BG. So this will be equal to 2 into half into AD. We know AD is 12 centimeter and BG is 6 centimeter. This will be equal to 72 square units or 72 units, right? 72 units. Just if you know, if you could recall all the area, all the formulae, all the concepts, that is enough. You can solve this. Any question as far as geometry is concerned. That is the beauty of geometry. Nothing is required, just learning the concepts and knowing how to apply them, clicking the right concept at right time. That is enough. And in some mocks, in most of the mocks that are available in the market, you can you can find there are super difficult questions in the actual mocks, in the mocks that you are attempting right now, right? That much difficulty is not required. Actually, that much difficulty is not required, and you are making a direct comparison with those mocks with the actual CAT, which is wrong. The difficulty level of CAT shouldn't be compared with the difficulty level of the mocks that you are attempting, and the scores that you are scoring now shouldn't be compared with the actual scores of your CAT. Don't be very much discouraged even if you score less in mocks right now. All right, but in the actual exam, your presence of mind is more important than the difficulty level. Which question to attempt, which question to leave, you must have that presence of mind. If you do not have that clarity, then it will definitely kill your time, which is not advisable at all. That leads to panic, right? You will be panic. Don't panic. Just observe the mocks. Don't attempt mocks, just observe the mocks. Which one to attempt, which one not to attempt. Just skip the questions one by one, just observe the questions one by one. All right, let us start with polygons. See, as far as geometry is concerned, each and every topic is important. It's not that particular topics like only triangles or only circles or the combination of triangles and circles are important. There is nothing like that. If you understand the quadrilaterals, if you understand the concept of the polygons and everything, circles, triangles and everything, then only you can be very much confident about geometry. Because if there is any combination, if there is any question which has a combination of a quadrilateral and a circle, and if you are not aware of quadrilaterals or the concept behind quadrilaterals, right, then you will be in a trouble. So you must understand each and every concept and try to solve as many questions as you can. So let us delve into the concept of polygons. So what is a polygon? A polygon is just a two-dimensional figure, right? It's a two-dimensional figure which has a finite number of straight lines, and those straight lines form sides of the polygon. For instance, so a polygon is a two-dimensional figure, and this has got a finite number of straight lines, and also these straight lines are the sides of the polygon. So let us look into some types of polygon. There are basically two types of polygon as far as the angles and lengths are concerned. We can also categorize polygons in some other ways. We will look into them one by one. So basically there are two polygons, regular and irregular. Regular polygons are the ones which have the angles, all the angles equal, and all the sides are also equal. For instance, we have a polygon here. All the angles in the polygon are equal. So this is 108 degrees, this is 108 degrees. So each and every angle, internal angle, is 108 degrees. And if we look at the sides, for instance, if this is 5 centimeter, then each and every side will also be a 5 centimeter, because this is a regular polygon. So in a regular polygon, the angles are equal and all the sides are also equal. And what about irregular polygon? If angles are not unequal, and if sides are also unequal, then it is an irregular polygon. And we can also classify polygons as convex and concave. So what are convex polygons? So all the internal angles in a convex polygon, all the internal angles definitely be less than 180 degrees. For instance, we have two figures. This is the example of convex polygon, because if you look at the angles that are formed, so each and every angle is definitely less than 180 degrees, right? This is a straight line, this has got 180 degrees, so it is moreover acute, right? So less than 180 degrees. And what about the concave polygon? In a concave polygon, we can observe at least one angle to be more than 180 degrees. So if you observe these angles, this is less than 180, less than 180. So all are less than 180 except this. This is greater than 180, right? So in a convex polygon, each and every internal angle will be less than 180 degree, and in a concave polygon, at least we have one internal angle which is greater than 180 degrees. And we can also differentiate convex and concave polygon in one more way, which is, let me draw a line like this, for instance. So in how many points is this line touching? In 2 points, right? This is the first point, this is the second point in which the line is meeting the polygon. It's meeting in two different areas, two different points. Whereas if I draw a line here, right, in a concave polygon, then it touches at 4 areas, right? This is the first, second, third and fourth intersecting area. So if we have a line touching a polygon in more than 2 areas, right, then that polygon is known as concave polygon. We can also define concave polygon in this way, way also. And this is one more way to classify polygons, in which the polygons are classified as simple and complex. So a simple polygon has got just one boundary and it doesn't cross over itself. So it's a simple polygon. But whereas a complex polygon intersects itself. For instance, star is a complex polygon. This is also a complex polygon because this polygon itself is intersecting. It intersects itself. Generally, complex polygons are not important for the exams, for all the MBA entrance exams, but the one complex polygon that we have to remember is star. And one point that you have to remember is sum of the angles of a n-pointed star. How can we calculate this? For instance, if we have this star, right? So the sum of all these angles, this is angle 1, 2, 3, 4, 5 and 6. So the sum of all these angles can be calculated by using this formula, n minus 4 into pi, where n is the number of points. So here how many points are there? This is a 6-pointed star. This is the first point, second, third, fourth, fifth and sixth. So we can calculate as 6 minus 4 into pi, which is equal to 2 pi. We know pi is equal to 180 degrees. So 2 into 180, this is equal to 360 degrees. So sum of all the internal angles of the star, right, of this star is 360 degrees. If it is 8-pointed star, then you have to substitute 8 in the place of n. So depending upon the number of points that the star makes. So this is the thing that you must remember as far as the complex polygons are concerned. So next we shall look into regular polygons. So now we are dealing with regular polygons. Let us construct a regular polygon. Let's say a regular polygon of vertices 5. So we got a regular polygon of vertices 5. Now we shall calculate the internal angles of this polygon. So what is the measure of each and every angle? So this is 108 degrees and this is 108. This is 108 degrees and this is 108 and this is one more. So all the angles are, each and every angle is 108 degrees, right? So the first thing here to note is the sum of all the internal angles in a regular polygon they are equal, right? And how can we calculate the sum of internal angles? So sum of internal angles is calculated by using the formula n minus 2 into 180 degrees, right? So let us calculate for this polygon. So we have, where n is the number of sides. So here we have how many sides? Here we have 5 sides. So let us substitute 5 minus 2 into 180 degrees. This will be equal to 3 into 180, which is 540 degrees. So these are the this is the total sum of the internal angles of this polygon. Or if we calculate manually, so 108 into how many are there? 5. So 108 into 5, this is also equal to 540 degrees, right? So sum of internal angles of any polygon, any regular polygon. So this is applied, please be very careful, this is applied only for regular polygons. So sum of internal angles can be calculated by using n minus 2 into 180 degrees. But what about external angles? Can you just tell me in a regular polygon what is the sum of the external angle as well as the internal angle? Sum of external plus internal. Just think about this. See, if I extend this line, right? If I extend this, right? If I extend this, this is my external angle. And if you also observe, this is a linear, this is a straight line, right? So straight line always forms a linear pair. So 180 degrees. So this is already 108 degrees. So this angle will be 180 minus 108. So this will be 72 degrees. 72 degrees. In the same way, this is my external angle. So this will be one more 72 degrees. And here, so like this, we will get all the external angles sum to be 360 degrees. So we can say that sum of one exterior angle plus the sum of the interior angle will be always be equal to 180 degrees. So here the interior angle is equal to 108, right? And the exterior angle is 72 and they sum up to 180. If the interior angle is 110, then the exterior angle will be 70. So they will again sum up to 180. So the sum of interior angle plus the sum of the interior angle and the exterior angle will definitely be 180 degrees. So what is the sum of all the interior angles? We know sum of all the interior angles of this regular polygon is 540 degrees. Then what is the sum of all the exterior angles? So exterior angles of this regular polygon is 72 into how many angles are there? 5. So 72 into 5, this will be equal to 360 degrees. This is not only applicable for this regular polygon, this is applicable for any regular polygon. So sum of exterior angle of any regular polygon, right? Sum of exterior angles of any regular polygon is equal to 360 degrees. Please make a note of it. So these are the things that you must remember. So we can calculate each interior angle by using sum of the interior angles, right? Calculating all the sum by n. What is n? N is the total number of sides. So in the previous slide we discussed how to calculate the sum of interior angles. Sum of interior angles can be calculated by using n minus 2 into 180 degrees by the total number of sides. And each exterior angle is calculated by 360 degrees by n. So we will apply all this so that you will understand in a even better way. And number of sides of a polygon, of a regular polygon, is calculated by 360 degrees by each exterior angle. For instance, see, this also makes a kind of sense because each exterior angle is equal to 360 degrees by n. So
n will be equal to 360 by each exterior angle. So these two are correlated. So these two are same. Just for the sake of understanding, I have just redefined them. So how can you apply this formulae? You can apply. See, I will just move this. See, if a question is given like this. So a question is given like this. A regular polygon has each internal angle as 120 degrees. Find the number of sides. So how can you do? The internal angle is 120 degrees. That's fine. So to calculate number of sides, we can calculate by, if we know the value of each external angle, because n is equal to, say this, 360 degrees by each external angle, but we do not know the external angle, we only know the internal angle, right? But we learned here, right, the sum of one exterior angle plus one interior angle, right? These two must make 180 degrees, right? These two form a linear pair. So if the interior angle is 120 degrees, then the exterior 30 degrees. So the 60 plus 120 is equal to 180. So each exterior angle, we know each exterior angle of this regular polygon is 60 degrees now. So we know that. So by using this, we can calculate the number of sides. N is equal to 360 by each exterior angle, which is 60. This is equal to 6. So this polygon has 6 sides. So a polygon with 6 sides, what is that? It's a regular hexagon. So the polygon that these guys are speaking about is regular hexagon. So polygon with 6 sides. And one more thing that you must observe here is, first let me clear all this. Yes. Do you observe any changes? Now do you observe any changes? No, you don't. We don't observe any changes, because whether we shrink this polygon or we enlarge this, the internal angle of the polygon remains same, and there is no change in the sum of one internal angle and the sum of the external angle, right? The sum of internal angle and the external angle remains same. The sum will be 180 degrees irrespective of the size of the polygon. And all the formulae that we discussed now apply for only regular polygons. Don't get confused. Now the next polygon that we will be dealing with is hexagon. Hexagon is a special polygon, because you will know why it is a special polygon. So let's construct the hexagon now. So hexagon is a 6-sided polygon, we know that. So let us construct a 6-sided polygon. Right, so this is my hexagon. So now just observe, I'm joining these two lines, right? So this is my line segment. The opposite vertices, I'm joining the opposite vertices. So this hexagon is divided into how many parts? 1, 2, 3, 4, 5, 6. So 6 equal parts. And if you observe, these 6 are equilateral triangles. Right? The 6 are equilateral triangles. This is the speciality of the regular hexagon. Whenever we join the opposite vertices will form equilateral triangles. Hence, it is easy to calculate the area of a regular hexagon. Let us derive the area of regular hexagon. Area of this regular hexagon, we know area is equal to 6 into. So this area is equal to the sum of all the areas of 6 equilateral triangles. So sum of the first equilateral triangle, second, third, fourth, fifth and sixth. So 6 into the area of equilateral triangle. We know the formula to calculate the area of equilateral triangle. What is that? Root 3 a square by 4. So let us cancel these two, and we will get 3 root 3 a square by 2. So area of regular hexagon can be calculated by using 3 root 3 a square by. For instance, so if you forget this formula, then in exam you can just derive this, but it is always better to remember some standard formulas. It's better to remember some standard formulas so that it will be more convenient while solving different problems where different concepts are involved. Well, now you may have doubt whether these are equilateral triangles or not. So for that, let me calculate the areas of all these. So this is 60 degrees, this is 60, this is, so if we take the included angle of these two, so this is one more 60. And so if you observe each and every angle, right, each and every angle is 60 degrees, and each interior angle of a hexagon, each interior angle is 120 degrees. However, the sum of interior plus exterior, sum of interior and exterior angle will remain same, will be 180 degrees, because if you extend this line, this must form a linear pair. So 120 plus this must be 60 degrees. So this is interior, this is exterior, exterior plus interior angle is equal to 180 degrees. This is fixed. But one thing here what we must understand is the interior angle of a regular hexagon is always 120 degrees. This is what we must observe, because the interior, because 6 equilateral triangles are formed, right? So each angle of the equilateral triangle is 60 degrees, which means this angle is equal to 60 and this angle is equal to 60, one more 60. So 60 and 60 will comprise 120 degrees, right? Will give us 120 degrees. So this will be my internal angle, and the external angle will be 60 because they both are linear pairs. They both form a linear pair angle. So these are the things that you must make a note of as far as the regular hexagon is concerned. First of all, hexagon is a 6-sided polygon, and each interior angle in a hexagon is 120 degrees and each exterior angle is 60 degrees. And when the vertices are connected to the center, then 6 equilateral triangles are formed, and the area of a regular hexagon is calculated by using the formula 3 root 3a square by 2. So let us just summarize what we have learned now. So in a regular polygon, right, we learned that the sum of external angles, right, the sum of external angles of a regular polygon is always 360 degrees. And what about internal angles? Internal angles can be calculated by using n minus 2 into 180, right? N is the number of sides of the polygon. Number of sides of the polygon. And how can we calculate number of sides? Number of sides can be calculated by 360 degrees divided by each external angle. Each external angle. In case we know the ratio of internal and external angle, or the values of the internal and external angle, then we can directly calculate by using 2 into internal angle by external angle plus 1. So 2 into internal angle by external angle plus 1. This is one more formula to calculate the number of sides. So I is the value of each internal angle and E is the value of each external angle. So number of diagonals. How can we calculate the number of diagonals of a polygon, of a regular polygon? So n into n minus 3 by 2. And what about area? Area can be calculated by using na square by 4 into cot 180 by n. So we can there are some ways to derive this, but I'm not interested to derive this now because that's not really important for the exam. So you can just remember this formula. Area of a regular polygon can be calculated by using na square, where n is the number of sides and a is length of each side. So n is the number of sides of a polygon and a is the length of each side of the polygon, right? So by using this we can calculate the area. For an octagon, specifically for an octagon, right, the area can be calculated by using 2a square plus into 1 plus root 2. So this is how you can calculate the area of an octagon. Octagon has 8 sides. So 2a square into 1 plus root 2. So polygon and names. So you all are aware of the number of sides and the respective names of the polygons. Just I will quickly summarize each and everything. If the number of sides of a polygon are 3, then it is known as a triangle, right? Triangle. If the number of sides are 4, then it is known as a quadrilateral. If the number of sides are 5, it is a pentagon, right? It's a pentagon. If the number of sides are 6, it is a hexagon. If the number of sides are 7, right, then it's a heptagon. And the polygon with 8 sides, it is an octagon. The polygon with 9 sides, it's a nonagon. And the polygon with 10 sides is a decagon, right? So let us summarize what we have learned under regular hexagon. So we have seen that each external angle of regular hexagon, right, each external angle is 60 degrees, right? Each internal angle is 120. Why each internal angle is 120? Because regular hexagon, 6 equilateral triangles are formed, right? 6 equilateral triangles are formed. So each angle of the equilateral triangle is 60 degrees. So two angles, internal angle has two angles will form 120 degrees. So if the internal angle is 120, the external angle must be 60, so that they both will sum up to 180 as they form a linear pair. So each internal angle of a regular hexagon is 120 degrees. If you are not clear about it, just you can watch the part of the video that we have discussed under the regular hexagon previously. And the number of sides of regular hexagon, right? What are the number of sides? It's a 6-sided polygon. And how can we calculate the area of regular hexagon? It is 3 root 3 a square by 2. We derived this previously. And when the vertices are connected to the center, 6 equilateral triangles are formed. Alright, so we discussed this one also. Now let us solve this. Let A, B, C, D, E, F. Okay, so this is a regular hexagon with each side of length 1 centimeter. The area of this square with AC as one side is. Alright, so this is, let us take this as A, B, C, D, E and F. Alright, so this is a regular hexagon, which means all the sides are of equal length and the length is 1 centimeter. Each and every side is 1 centimeter. The area of square with AC as one side. So AC, what is AC? Let me connect AC first. So this is AC. AC is a side of a square. So let us do one thing. Let us draw a perpendicular line. Let us draw a perpendicular line. So this bisects AC. This bisects AC and also it makes 90 degrees at the point of intersection. Right? It makes 90 degrees. And if you observe triangle CBA, CBA is an isosceles triangle. Why is it an isosceles triangle? BC is equal to 1 centimeter. BA is also equal to 1 centimeter. So two sides are equal. Two sides are equal. Which means two angles must also be equal. Right? Two angles must also be equal. And why CA is equal? CA is divided into two equal parts. So if you remember in an isosceles triangle, if we draw a median, right? If we draw a median, that median, that line is equal to the angular bisector, that is equal to the perpendicular bisector, that is equal to the altitude, everything. So this is also equal to a median. So median divides a line in two equal parts. AC is exactly divided into two equal parts. So this is an isosceles triangle. We are clear about it. And this is 90 degrees. And we know the internal angle of a hexagon. What is that? Internal angle of a hexagon. It's 120 degrees. See, where is it? Internal angle of a hexagon. Yes, see, internal angle of hexagon is 120 degrees, which means we can say that this is 60 and this is 60 because this is the median, this is the angular bisector, and the angular bisector divides the angle into two equal parts. So this is 60 degrees and this is one more 60 degrees. If this is 90, this is 60, then this must be 30 degrees, this must be 30 degrees, right? Which means let us take this triangle separately. The moment you hear or you look at 90-60, then the ratio that you must recall is 90-60-30 ratio, right? So this is 30, this is 90, this is 60, and let us take side opposite to 60 degrees is as 60, side opposite to 30 degrees is as 30, and side opposite to 90 degrees is obviously the hypotenuse, right? And what is the ratio? The ratio of the hypotenuse, the 90-60-30 ratio. The hypotenuse side opposite to 60 and side opposite to 30. 90-60-30 ratio is 2:√3:1, right? I hope you all remember this. So 2:√3:1, this is the ratio, and we know the opposite side of this 90 degrees is 1 centimeter. So if this is 1 centimeter, then side opposite to 60 degrees, right? So this side must be √3/2. So if this is √3/2, this is also √3/2. So let us mark this as n. So nc is √3/2, na is also √3/2, and we are asked to find the area of a square with, okay, so if we find out AC as this is one of the sides of the square, we can easily find out this area of the square, which is a square. So let us calculate for AC first. So √3/2 plus √3/2, which is 2√3/2, again it's √3, right? So side is equal to √3, and area is equal to square of the side. So √3 squared, this is equal to 3. So 3 is our answer. Hope this is clear to you. So this is there's nothing here. The only thing is, the moment you look at a hexagon, all the properties that we have discussed, all those must just strike your mind. The internal angle, the sum of the, of course, the sum of the internal exterior angle, you know that is going to be 180 degrees. The internal angle of a hexagon, regular hexagon, is 120, and the isosceles triangle property, which is the two equal sides and two equal angles are always equal, and the median isosceles triangle has got a line which is the median, the angular bisector, the perpendicular bisector, and everything. That is the one more thing that you must remember. And this ratio, predominantly this is the ratio that you must remember. It's not 90-60-30, and there's one more ratio, which is 90-45-45. So these two will be used extensively as far as MBA entrance exams are concerned. It can be CAT, it can be XAT, it can be any other non-CAT exams too, right? Let us solve one more question. Let A and B be two regular polygons having A and B as sides. Alright. So A and B, capital A and B are the two regular polygons, and small a and small b are the sides respectively. So if B is equal to 2A, if side B is equal to 2 times of side A, and each interior angle of B is 3/2 times each interior angle of A, then each interior angle in degrees of the polygon with A plus B sides is. Alright. So let us take the polygon A here and polygon B. Okay. Now there is something given as far as the sides are concerned. What is that? Sides, a relation is given, right? So sides of A, polygon A is A, and sides of polygon B is B. I mean, the number of sides of polygon A is A, the number of sides of polygon B is B. However, the relation is also given. B is equal to 2A. So let us cut this. B is equal to 2A. So it's also given that each interior angle of B is 3/2 times of each interior angle of A. So how can we calculate interior angle? Interior angle of a regular polygon we learnt interior angle can be calculated as n by 2 into 180 degrees by n. Check this previously. So n minus 2 into 180 degrees by n. So in the place of n, so what is n? N is the number of sides. So here polygon A has a number of sides, polygon B has 2a number of sides, double that of polygon A. So we can just simply substitute. So each internal angle, right, each internal angle can be written as n minus 2. So instead of n, I am directly writing a. So a minus 2 into 180 degrees by a. But the relation is each interior angle of B is 3 by 2 times each interior angle of A. So 3 by 2 times of each interior angle of A. So interior angle of B can be calculated as 2a minus 2. Just I'm substituting 2a in the place of n. Don't get confused. So this is 180 by 2a. So we shall cancel all this. So 2 and this is 90, right? And we can cancel these two. So if you cancel, you will get the answer as 3a minus 6. This is equal to 2a minus 2 and a is equal to 4. A is equal to 4. But we are asked to find out the interior angle, right? Interior angle of the polygon with a plus b sides, not a plus b sides. So we know a is equal to 4. What is b? B is 8, right? B is 8. So 2 into a is 2 into 4. 2 into 4 is 8. So 4 plus, so we are asked to find a plus b sides. So a plus b is 4 plus 8. So 12. So we are asked to find out each interior angle of a 12-sided polygon, right? 12-sided polygon. How can we calculate the interior angle? By using the same formula. But here now instead of n, we have to replace n with 12. 12 minus 2 into 180 degrees by 12. This is equal to 150. So 150 is our answer. 150 is the each interior angle of the polygon having 12 sides, right? So quadrilaterals. This is the next concept, important concept. So what are quadrilaterals? There are a lot of figures that come under quadrilaterals. So simply quadrilaterals means they are four-sided polygons, right? They can be a parallelogram. The quadrilaterals can also be trapezium. It can be kite, rectangle, rhombus, square, isosceles, anything. So the condition is they must be four-sided polygon, right? So we will look into how the quadrilaterals are divided and how can we remember them easily with a good mind map. Okay, I will tell you that, don't worry. So we are dealing with quadrilaterals. So I have just taken a quadrilateral and we shall observe some properties. So this is a quadrilateral of ABCD, right? ABCD. Now if I draw a diagonal of this quadrilateral, right? So AC is a diagonal of this quadrilateral, and if I draw one more diagonal which is DB, right? DB. So from this you can understand that to calculate the area of quadrilateral there is no specific formula. Of course there is a formula, but that formula is derived by calculating the individual areas of these two triangles. What are the triangles? DAB and BCD. So calculating each area of the triangle and adding up will lead us to the area of the entire quadrilateral. So how can we calculate the area of the triangle? DAB, half into base into height. Here if we take base as DB, so DB is a diagonal, and if we consider DB to be base, what is the height? Let us draw the altitude. So AE is the height right, of the triangle DAB, and for the second triangle, which is DBC, what is the height? Let us draw one more altitude. So this is the height of the triangle DCB. Now we can calculate the area of the quadrilateral easily. So let us calculate the area of the quadrilateral. Let me move this first. Let me move this quadrilateral a little bit. Okay. So area of quadrilateral ABCD, right? ABCD is equal to area of triangle ABD plus the area of triangle BCD. Hope it's clear. So AE is height of the triangle ABD, and H2, which is FC, is the height of triangle BCD, and DB is the base of both the triangles, and I named it as D1. So what is the area of triangle ABD? Half of base. What is base? DB, which is D1. D1 into half of base into height. Height is H1 plus triangle, area of triangle BCD. BCD is half of base. Base is again D1 because that is common base to both the triangles, into height. What is height? H2. And if we take half and D1 as common, right? D1 as common, then it will be H1 plus H2. So this is the area of quadrilateral. Area of quadrilateral can be calculated by using this formula, half D1 into H1 plus H2. Alright. Now there is one more formula to calculate the area of quadrilateral. If we have angle, if we have theta, which is half D1 D2 into sine theta, we can use that, but it depends on the situation. So in what kind of situations can we use that? See, let us say if we have this angle as theta, right, and this will be also this is also theta because these are vertically opposite angles, and if this is theta, this will be 180 minus theta because these two, right, these two, this one and this one will be a linear pair, and if this is 180 minus theta, this is also 180 minus theta because these are vertically opposite angles again. So this whole diagonal is D1 and this whole diagonal is D2, and we have two parts. Let us divide this diagonal into two parts. Let us name this one as D2B, and from this midpoint to here as D2A. Alright, D2A. Now what is sine theta? Sine theta is opposite side, which is H2 by the hypotenuse, which is D2A. So sine theta is H2 by D2A. Now H2 is now equal to D2A sine theta. So this is sine theta for this part, and if we calculate sine theta for this part, then we will be getting sine H1 is equal to D2B sine theta. D2B sine theta, because this will be the hypotenuse and this will be the H1 will be the opposite side in that case. So H2 and H1 we got. Now just substitute in this half D1 into what is H1? H1 is D2B sine theta plus H2 is D2A sine theta, right? Now this is equal to half D1 D2 sine theta. So this is one more formula to calculate the area of quadrilateral. So this derivation and all this is not important, but how we derive, right? Just the observation is important. For the purpose of the exam, that you can just remember these two formulae. So this is the first observation that we made by calculating the area of the quadrilaterals. And the second observation is, let us calculate let's measure the angle, let us measure. So this angle is 95.8 degrees, and if we measure, this is 107.2, and this angles measure is 82 point something. Let me bring this. Okay, 74.9 and 82.1, 107.2, 95.8. So did you observe anything? If we sum up all these angles, this will lead us to 360 degrees, and all these angles are interior angles, right? So sum of interior angles of a quadrilateral is always 360 degrees. This is one more observation that we all must make.
So let us summarize what we have learned. The general properties of the quadrilaterals. So we know the internal angles of the quadrilaterals is always 360 degrees, right? All the internal angles sum up to 360 always. And the area is equal to sum of two triangles of a quadrilateral. So we have two formulae for that. The first one is half d1 into h1 plus h2, where d1 is the diagonal and h1 and h2 are the heights of the two triangles, and the second one is half d1 d2 sine theta, where the sine theta, the included angle, is given, right? When included angle is given, we can directly apply this formula to calculate the area of the quadrilateral. And one more property is, if we circumscribe the circle, right? For instance, if we take a circle, let us take a circle here. So if this is a circle, so think it as a circle. Now this is A, this is B, this is C, and this is D. A, B, C, D are the sides of the quadrilateral, right? Now in a quadrilateral, this is a quadrilateral and this is circumscribed by a circle, right? Then the property is the opposite sides, the sums of the opposite sides are equal, which means A plus C is equal to D plus B. Alright, A plus C, this sum is equal to D plus B, the opposite sides. This is valid only when a quadrilateral circumscribes a circle, right? Or a circle inscribes a quadrilateral, right? Only in this condition the opposite sides A plus C is equal to the other pair of opposite sides, which is D plus B. Now diagonal properties. The diagonals of a quadrilateral need not be equal. For instance, this is point A, B, C and D, right? AC need not be equal to BD. I am not telling AC won't be equal to BD. AC need not be equal to BD, right? And these two diagonals need not bisect, and these two diagonals need not bisect the vertex angles, right? These need not bisect the vertex angles, need not be the angular bisectors. So let me write it. Need not be equal, need not bisect, need not bisect each other, okay, and need not bisect the vertex angles. Alright, so these three are the diagonal properties of any quadrilateral. Cyclic quadrilateral. Now this is somewhat interesting because, see, let us see why this is interesting. Let me take a cycle first. Circle, okay. So what are the properties that are applied for a general quadrilateral? Most of the properties are also applied for cyclic quadrilateral. Besides these properties, there are some additional properties which we will learn now. So the first property is sum of interior angles is equal to 360 degrees, right? The sum is always equal to 360. Let us say this is vertex A, B, C and D. So this is angle A, angle B, angle D and angle C, right? So angle A plus B plus C plus D is always equal to 360 degrees. The opposite angles are always supplementary. So in a cyclic quadrilateral, opposite angles are always supplementary, which means opposite angles sum up to 180 degrees.
For instance, if we have a cyclic quadrilateral like this, if this is 84 degrees, then this must be 96 degrees. If this is 96, right, if let us say this is 74, right, 74 degrees, then angle D must be equal to 106 degrees because opposite angles are supplementary, right? So this is a unique property of this cyclic quadrilateral, and the angle bisectors form a cyclic quadrilateral. For instance, angle bisectors form one more cyclic quadrilateral means, let us say this is the angular bisector, right? This is the angular bisector, and for A this is the angular bisector, right? For D this is the angular bisector, and for C this is the angular bisector. Now when we try to meet all this, right, when we try to meet all this area, let me highlight that with yellow color. So this part is one more cyclic quadrilateral, right? This part is again a cyclic quadrilateral. So the angular bisectors form a one more cyclic quadrilateral. So angular bisectors, when they are extended, form one more cyclic quadrilateral. And how can we calculate area of a cyclic quadrilateral? We know how to calculate area of a general quadrilateral. For this, for cyclic quadrilateral, area can be calculated as root of, right, root of. This is somewhat similar, not exact, but similar to Heron's formula, which is S into S minus A into S minus B into S minus C. But this is S minus A into S minus B into S minus C into S minus D. That's it. No additional S. Okay. This is directly S minus A into S minus B into S minus C into S minus D. This is how we calculate the area of the cyclic quadrilateral. So please make a note of all this. Here S is equal to the semi-perimeter as usual. So in triangle, S is equal to the sum of the sides by 2. The sum of the sides A plus B plus C by 2. Here one more side gets added because A plus B plus C plus D. The quadrilateral has 4 sides, so A plus B plus C plus D by 2. This is the semi-perimeter and the value of S. Ptolemy's theorem. So in a cyclic quadrilateral, this theorem talks about, in a cyclic quadrilateral, the diagonals, let us say this is D1, right, and this is D2. Okay, diagonal 1 and diagonal 2. The product of diagonals D1 and D2, D1 into D2 is equal to, right, let me mark this. Let's say this is A, this is B, this is C, this is D. A, B, C, D are the sides of the cyclic quadrilateral. Now these two diagonals is equal to the opposite, the sum of the product of the sides of the quadrilateral. So A into C, A and C are the opposite sides, so their product plus B into D, these two are the opposite sides, their product, and the summation of these two. Alright, so diagonal 1 into diagonal 2 is equal to the sum of the product of opposite sides of a quadrilateral, cyclic quadrilateral. This is Ptolemy's theorem, and this is applicable only in cyclic quadrilateral, not applicable in the remaining other quadrilaterals. So whenever you observe a cyclic quadrilateral, then it is highly impossible to skip Ptolemy's theorem and solve the question. Of course, there may be any other way to solve the question, but if we learn this concept, then it will be helpful in solving a lot of cyclic quadrilateral problems, because Ptolemy's theorem comes frequently as far as cyclic, whenever cyclic quadrilateral comes into picture, right? So the next quadrilateral is parallelogram. So let me take a parallelogram. So what are the properties of a parallelogram? So in a parallelogram, the opposite sides are parallel. So if we say AD and BC, right? If we take AD and BC, AD is parallel to BC and AB is parallel to DC, right? So the first property is, so opposite sides are parallel. And if you observe, opposite angles are equal. So angle A is equal to angle C and angle B is equal to angle D. So opposite angles are equal. And what is the next property? Adjacent angles. If you observe angle A and angle D, and whereas angle B and angle C. So 85 plus 95, this is 180. So 95 plus 85, this is again 180. So adjacent angles are supplementary. So adjacent angles are always supplementary. And this diagonal, if you observe, this is not exactly bisecting the angle, right? This is not exactly bisecting the angle. What would happen if it bisects the angle? Well, in that case, it will become a rectangle. So this is my rectangle. Each angle is 90 degrees. So these two are my angular bisectors. So each angle is getting divided exactly. So this is 45, this is 45. So each and every angle, so 90 degrees is getting divided into 45 and 45 degrees. So when the diagonals of a parallelogram exactly bisect the angle, then it will become a rectangle. So rectangle is also a parallelogram, but the difference is all the angles are 90 degrees in a rectangle, and also the angular bisectors bisect the angles exactly, right? And what happens if this parallelogram is inscribed in a circle? For instance, if we inscribe this parallelogram in a circle, right, this parallelogram will be adjusted in such a way that it will become a rectangle inside, right? So when it is inscribed, when the parallelogram is inscribed in a circle, it will become a rectangle. And what happens if we make this parallelogram circumscribing a circle? Circumscribing in the sense, circle is touching all the sides of the parallelogram. So if the circle is touching all the sides of a parallelogram, then this parallelogram will become a rhombus. So when a parallelogram is circumscribing a circle, then that parallelogram becomes a rhombus automatically. Well, what is a rhombus? In rhombus, all the sides are opposite sides are parallel, right? All the sides are equal, right? In a rhombus, we will deal with rhombus in the upcoming slides, but for now I will just explain you the basic properties. So opposite sides are always parallel in a rhombus, and all sides are equal. So these two are the basic properties of a rhombus. And whenever we circumscribe a circle, when this parallelogram circumscribes a circle, then this parallelogram will be adjusted and will become a rhombus, right? When it is inscribed a circle, when this parallelogram is inscribed in a circle in which the circle will be outwards, so when it is inscribed, it will become a rectangle. When it is circumscribing a circle, it will become a rhombus. And in a parallelogram, adjacent angles are supplementary, opposite angles are equal, and opposite sides are parallel. So these are the basic general properties that you must remember. And how can you calculate the area of the parallelogram? Area of the parallelogram can be calculated by base into height, BH. Area is equal to BH, and if the angle is given, the included angle is given, then you can calculate by using AB sine theta, where A and B are the sides of the parallelogram. So AB sine theta and BH are used to find the area of the parallelogram. Now this point is important. Sum of areas of opposite triangles formed by any point inside the parallelogram are equal. For instance, if we take this parallelogram, right, and if we put a point somewhere here, so if we put some point here, right, so by using this point we can form two triangles. This is one triangle, this is one more triangle, and if these two triangles are formed, automatically two more triangles will be formed on opposite sides. So this is triangle 1, this is triangle 2, triangle 3, and triangle 4. Now according to this property, sum of areas of opposite triangles formed are equal. For instance, what are the opposite triangles? T2 and T4, T3 and T1, right? So T2 plus T4. So area of triangles T2 plus T4 is equal to area of triangles T1 plus T3. Now let us look into the diagonal properties of a parallelogram. So the diagonals need not be always equal, right? So the diagonals need not be equal. Here AC is a diagonal and BD is a diagonal. So diagonals can be equal, diagonals may not be equal. If diagonals are equal, it will become a rectangle. If diagonals are not equal, it will become a general parallelogram. In rectangle also is a one more case that is included in parallelogram. So if it is not equal, diagonals need not be equal, and diagonals bisect, right? They bisect. So AC bisects BD, and diagonals need not bisect at right angles. So here this angle, right? This angle need not be 90 degrees always. And one more diagonal property is these diagonals need not bisect at vertices. If they bisect, then it will become a rectangle. Because they exactly make 90 degrees, they bisect into 45 and 45 degrees. So in that case, it will become that parallelogram becomes a rectangle. Now both diagonals divide the figure into two pairs of congruent triangles. So two pairs. So A, if we name this as O, this intersecting point. So AOB, DOC, right? AOB is my one triangle, DOC is my one more triangle, BOC and AOD. So four congruent triangles by congruency, all the sides are equal and the angles are also equal. So all the four sides have equal area as the diagonals divide the parallelogram into two pairs of congruent triangles. So let us solve this question now. In a parallelogram ABCD of area 72 square centimeter, the sides CD and AD have lengths 9 centimeter and 16 centimeter respectively. Let P be a point on CD such that AP is perpendicular to CD. Then the area in square kilometer okay, it must also be in square centimeter, right? So the area of triangle APD is, so this is a parallelogram A, B, C and D. So here it is given that CD is equal to 9 centimeter. So CD is 9 centimeter and AD is 16 centimeter. AD is 16 centimeter. Let P be a point on CD. So let P be a point on CD such that AP is perpendicular to CD. So if we have to place point P in such a way that AP is perpendicular to CD. So AP is perpendicular to CD. Okay, let us take this point as P and it is perpendicular to CD. Now we are asked to calculate the area of triangle AP and D. So this area must be calculated. We know that ABCD is a parallelogram. So we discussed how to calculate the area of parallelogram. How to calculate? Area is equal to, here we do not have any angle. So we can directly take the first case, base into height. Right? Area is equal to base into height. Area is already given here. Area is 72 square centimeter and base. What is base? Base is DC, which is 9 centimeter, into what is height? Height is AP in this case. So we did not know that. So let us take it as AP as it is. So AP is equal to 72 by 9. This is equal to 8. So we know that AP is equal to 8 now, 8 centimeter. So now it became, as it is a triangle, we can calculate the area of the triangle APD is equal to half into what is base? Base is, we can calculate base DP by using the Pythagoras theorem, because this is 90 degrees and the side opposite to 90 degrees is a hypotenuse. It must be hypotenuse. So 16 square is equal to 8 square. 16 square is equal to 8 square plus dp square. So 16 square is 256 minus 8 square is 64 is equal to dp square. Now dp is equal to root of 192. So 192 is equal to 8 root 3.
So dp is equal to 8 root 3. So dp is equal to 8 root 3, and we can calculate the area. Area of triangle ADP is equal to half into what is base? Base is 8 root 3, and what is height? Height is 8 centimeter. So this is equal to, just cancel them. So 8, 4, this is 32 root 3. So area of triangle ADP is equal to 32 root 3. Now let us get into rhombus. So in a rhombus, so I just have taken a rhombus. So opposite sides are parallel. So AB is parallel to DC, and BC is parallel to AD. And the next property is all the sides are equal. AB, BC, CD, DA. The measurement of all the sides are equal. The measurements are equal. And if we consider angles, there is no specific property, but whatever the properties of parallelogram are there, those properties are applied. They can be applied in rhombus too. So opposite sides are parallel and all sides are equal, right? And how can we calculate the area of rhombus? Area of rhombus can be calculated as, if we consider AC as D1 and DB as D2, diagonal 2 and diagonal 1. So area is equal to half D1 D2. So actually it's half D1 D2 sine theta, but here as it is bisecting, the diagonal is bisecting at 90 degrees. So sine theta, sine 90 becomes 1, so it remains half D1 D2. And one more observation here is, when it is inscribed in a circle, right? When this is inscribed in a circle, or when a circle circumscribes it, then this rhombus will modify, right? This rhombus gets modified. It will get modified into a square. It will get modified into a square when this is inscribed in a circle. When rhombus is inscribed in a circle, it will get modified into a square where each and every angle will be 90 degrees, and the diagonals are equal, and the sides are also equal. If we look at the diagonal properties, the diagonals need not be equal, right? In a rhombus, the diagonals need not be equal, and they bisect at 90 degrees. So when these two diagonals bisect each other, 90 degrees is formed exactly at the center, right? So diagonals bisect at 90 degrees, and diagonals also bisect the vertex angles. So they also bisect the vertex angles. And just by observing, we can say that the rhombus is dividing, the diagonals of a rhombus are dividing this rhombus into 4 congruent triangles, like in the previous case, the case of parallelogram. And these 4 triangles are congruent, which means the area of these 4 triangles is always equal. So rhombus gets divided into 4 congruent triangles by the diagonals. So these are the general properties and the diagonal properties of a rhombus. So in this case, let us mark O as center. Area of triangle AOB is equal to area of triangle BOC is equal to area of triangle DOC and area of triangle AOD. So let us delve into rectangles, the general properties of rectangles, and all are aware, I think, and all must be aware of the general properties by now. So let us take ABCD as a rectangle. The sides opposite, right? The opposite sides are always parallel and equal. So DC is always parallel to AB and BC is always parallel to AD. So opposite sides are parallel and equal, and angles, each and every angle is 90 degrees at the vertex, right? This is 90, this is 90. And angle bisectors form another rectangle. For instance, if we bisect this, right? This is an angular bisector, this is an angular bisector, right? And this is one more angular bisector from vertex P. If we bisect these, and if we form, right, if we take all the angular bisectors,
then at the center one more rectangle will be formed, right?
So these are the general properties. Opposite sides are parallel and equal, all angles are equal to 90 degrees, and the angle of bisectors form another rectangle. And what are the diagonal properties? The diagonals of the rectangle are always equal, right? In this case, DB is always equal to AC, right? Diagonals are equal always. And diagonals also bisect. Need not bisect at 90 degrees, but diagonals bisect. So they bisect and need not at 90 degrees.
And how can we calculate the length of diagonal? Just observe this. If we take AC as D, right? AC as D, AB is the length of the rectangle and BC is the breadth of the rectangle, right? By observing this, we can say that ACB is a right angle triangle, AC being the hypotenuse. So AC, we have taken this as D, so D square is equal to L square plus B square. So D square is equal to L square plus B square. So D is equal to root over L square plus B square. So this is the formula to calculate, to know the value of the diagonal. So this is how we calculate the diagonal of a rectangle. So let us look into the next parallelogram, which is a square. And we know in a square all the sides are equal and all the opposite sides are parallel, right? So AB is parallel to DC and AD is parallel to BC, and all the measurements of all the sides are always equal, and the angle at the vertex is always equal to 90 degrees. For a given perimeter of a quadrilateral, for instance, let us take this square. This is a rectangle, right? This is my kite, alright. This is my parallelogram, okay. If we have equal perimeter, if we say the perimeter of square is 30 centimeter and the perimeter of this rectangle is also 30 centimeter, perimeter of this kite is 30 centimeter, and perimeter of this parallelogram is also 30 centimeter. So when perimeter is equal for all the parallelograms, then the area will be maximum for the square. You got to remember this. When perimeter of all the parallelograms are equal, the area will be maximum only for the square. Let us take the other way around. What if the area is equal for all these parallelograms? If area is equal for all these parallelograms, then the perimeter will be minimum for the square, not maximum. Perimeter will be minimum for the square, alright. So if perimeter is equal, area is maximum. If area is equal, perimeter is minimum. And let us look into the diagonal properties. The diagonals are always equal, right? The diagonal AC is equal to diagonal BD, and they bisect at 90 degrees. So the angle that is formed at the center is always 90 degrees, and they also bisect the vertex angles. Diagonals also bisect the vertex angles, and these two diagonals divide the square into 4 congruent triangles. So this is my triangle 1, triangle 2, triangle 3, triangle 4. So all the 4 triangles are congruent, in which they have equal areas, right? And how can we measure the diagonal, the length of the diagonal? Diagonal can be measured. See, this is almost similar to rectangle. In a square, each and every side is always equal. So let us take A, right? So DB is the diagonal, right? So diagonal is equal to A square plus A square. D square is equal to A square plus A square. Now D is equal to root of 2A square, which is equal to A root 2, right? So this is how we calculate the diagonal of a square. D is equal to A root 2, where A is the side of a square. So let us solve this question. If ABCD is a square and BCE is an equilateral triangle, what is the measure of angle DEC? So ABCD is a square. So ABCD BCD is a square. BCE is an equilateral triangle. BCE. So E must be here. So BC is an equilateral triangle. And what is the measure of angle? DEC. 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 So let us join this. So we know that this is an equilateral triangle, which means all the angles are 60 degrees, right? Each and every angle is 60 degrees. This must be 60, right? And if you just observe, this is the common side of this equilateral triangle as well as for this square. If we assume that this length to be S, then this side BC must be S, right? BC is S, then DC is also S, CE is also S, each and everything is yes, same length. Now if two sides are equal, then two angles are also equal, because if two sides are equal, then this is an isosceles triangle, and in an isosceles triangle two angles are also equal, which means this angle is equal to this. And if you observe, this is a square. If this is a square, ignore this triangle as of now. This vertex is always 90 degrees. This vertex is always 90 degrees, right? This vertex is always 90 degrees. Now it is like this, right? Now it is like this. So this is 90, right? This is, this is 60, and we have these two triangles. This is triangle DC and E. This is 90 and this is 60, which is equal to 150, right? And we know sum of all the angles in a triangle must be equal to 180. So 180 minus 150 is equal to 30 degrees. Now this 30 degrees must be divided equally to angle D and angle E. So which means we can divide it in 15 and 15, right? So we are asked to find the measure of DEC. So DEC is equal to DEC. Angle DEC is equal to 15 degrees. So I will summarize the parallelogram, all the parallelograms that we have discussed as of till now. This is very crucial because the mind map that I am discussing now, right, it must stick in your mind. This mind map must stick in your mind so that it will be easier to recall, right? It won't be clumsy, it will be easier to recall. So first let me take the parallelogram. So this is my parallelogram. If this is actually divided into two types. First one is rhombus, right? Some properties of parallelogram will be taken by the rhombus, and some properties of the parallelogram will be taken by rectangle, right? Rectangle. Now if I combine the properties of both rhombus and rectangle, then it will become a square. Why? Let us take the properties of each and everything. See, in a parallelogram, opposite sides are parallel. So when opposite sides are parallel and equal, then what about the diagonals? So the diagonals need not be equal, and they bisect. The diagonals bisect, but need not bisect at 90 degrees. This is what you have to remember. Need not bisect at 90 degrees. Need not bisect at 90 degrees. Alright. Need not bisect at 90 degrees. And these diagonals need not bisect the vertex angles also. They need not bisect the vertex angles. So these are the properties of parallelogram. The opposite sides are parallel and equal. So the diagonals need not be equal. They will bisect. Diagonals will bisect, but need not bisect at 90 degrees. And the diagonals need not bisect the vertex angles too. So these are the properties of parallelogram. Now we shall look how these properties are different to rhombus and rectangle, and what are the properties that is similar to rhombus and rectangle. If we take the case of rhombus, if we take the sides of a rhombus, the sides are always equal. The sides of the rhombus are always equal. If we take the angles of a rhombus, angles need not be equal. And what about the diagonals? The diagonals need not be equal, right? The diagonals need not be equal. See, the diagonals of parallelogram need not be equal, of rhombus also need not be equal.
and the diagonals bisect at 90 degrees. This is how a parallelogram is different from rhombus. In a parallelogram, the diagonals need not bisect at 90 degrees, and if it bisects, then it will become a rhombus, right? It bisects the vertex angles. The diagonals bisect the vertex angles, and also the diagonals form a four congruent triangles in which the areas of all the congruent triangles are always equal. Now, what is rectangle? Let us look into the properties of rectangle. In a rectangle, let us look into the side properties. The sides need not be equal. The sides won't be equal, right? The sides won't be equal. All the sides won't be equal. And regarding the all angles are 90 degrees, right? Each and every angle is equal to 90 degrees. And if we consider the diagonal properties, all the diagonals are always equal. The two diagonals are equal, and the diagonals need not bisect, right? They need not bisect at 90 degrees. They will bisect, but need not bisect at 90 degrees. This is similar to the parallelogram, right? This property is taken from the parallelogram property, which is need not bisect at 90 degrees. They will bisect, however, need not at 90 degrees. But in the case of rhombus, they will bisect at 90 degrees, and they also bisect the vertex angles. But in a rectangle, again, need not bisect vertex angles. The same property comes here. Need not bisect vertex angles. Now, we shall combine the properties of rhombus and rectangle, and we shall make it for the square, right? Now, this will be very interesting if you observe the properties of the rhombus. What are the properties that are that the square is taking from rhombus, and what are the certain properties that are taking from the rectangle? The first property is all the sides are equal. Right? Now this property is taken from this square is taking this property from rhombus, right? All the sides are equal, and all the angles are 90 degrees. This property is taken from rectangle, right? The square is taking this property from rectangle. And what about diagonals? Diagonals are always equal. Now this is not taking from rhombus. This property is taking from square is taking from rectangle. Bisect at 90 degrees. The diagonals bisect at 90 degrees. Now this property is being taken from rhombus, not rectangle. Bisect at 90 degrees. Now four congruent triangles. The next property is the diagonals form four congruent triangles in which what is meant by congruency? All the areas of the triangles are always equal. So the diagonals form four congruent triangles. Now this property is being taken from rhombus. So square is nothing but the concoction of the properties of certain properties of rhombus and certain properties of rectangle, right? So this is a special case of the parallelogram. So generally the parallelogram has the diagonal properties and the side properties like this, right? If there is some modification in the properties, like all sides are equal and the angles need not be equal, and if the diagonals bisect 90 degrees, then it will become a rhombus. If not, it will become a rectangle. And if we combine the properties of rectangle and rhombus, then it will form a square. This is the mind map that you must recollect. All right. Now let us look into one more parallelogram, which is trapezium. What is trapezium? Trapezium is a four-sided parallelogram in which two sides are equal. Two sides are parallel, and we have two oblique sides. What are oblique sides? Oblique sides are non-parallel sides. In this case, these two are oblique sides, and these two are my parallel sides, right? These two are my parallel sides. Let us take this as A, B, C, D. So A, B, C, D is my trapezium, in which AB is equal to AB is parallel to DC, and AD, BC are oblique sides. So what are the general properties of of the trapezium? One pair is parallel. Only one pair is parallel. Only one only one pair of sides are parallel. So only one pair is parallel. Now if we join this line, right, if we join this line connecting two oblique sides at 2 points, let us name them as P and Q. So PQ is a line joining two oblique sides, right, two oblique sides. Now this line can be calculated, PQ can be calculated by using the formula half AB plus CD in this case. So line joining the midpoints of oblique sides. Line joining midpoints of oblique sides can be calculated by using half into AB plus CD, where AB and CD are my parallel sides. Alright. So if PQ is joining the midpoints of these oblique sides AD and BC, right? Like P is the midpoint of AD, Q is the midpoint of BC, and we can calculate the length of PQ by using this formula, which is half into the length of the two parallel sides, the sum of the lengths of two parallel sides. Now what happens if we inscribe this trapezium in a circle? If we inscribe a trapezium in a circle, then this trapezium will get modified in such a way that the oblique sides are also equal, right? The oblique sides will also be equal. So if the trapezium is inscribed, if it is inscribed in a circle, then it will become isosceles. Because opposite sides, the oblique sides, right? The oblique sides are equal. The parallel sides need not be equal. AB and DC need not be equal, but these oblique sides will be equal, in which it will become isosceles. Two sides being equal. Now if we say, right, if we just assume the distance from AB and PQ as n, right, this distance is n, and from PQ to DC this distance as m. So now what happens is, we can state that PQ is equal to m by m plus n into DC, and so let me write it here. So PQ is equal to m by m plus n into DC plus n by m plus n into AB. So this is the expression that we get when we have the distance between AB and PQ and DC. If we have only the lengths of AB and DC, we can directly calculate the length of PQ by using this formula, half into AB plus CD. In case if we have, right, if we have the lengths, the distance between DC and PQ and AB, right, as m and n, right, as m and n, and we know the length of PQ too, right, and we know the length of DC also, and if we are asked to find out the length of AB, then we can also use this formula too. Alright, so this is just a relationship between the distance of PQ and DC and PQ and AB with the parallel sides. So let us look into the diagonal properties of trapezium. We discussed, when this trapezium is inscribed in a circle, the oblique sides will be equal, right? The oblique sides will be equal, and if the oblique sides are equal, then the diagonals are parallel. Then the diagonals of the trapezium are diagonals of the trapezium are equal, right? And also the diagonals, let me write it here, the diagonals intersect in the proportion of the sides. Now what does this mean? Diagonals intersect in the proportion of the sides in a trapezium, which means if I construct a diagonal like this, let me join AC and DB. Alright. Now these diagonals intersect in the proportion of sides. So let us take the sides. We know the sides are AB, BC, CD and DA.
Now how are these diagonals intersecting? Let us mark the intersecting point as E, right? This is E, intersecting point of two diagonals. So from this property we can say that AE by EC is equal to BE by DED, BE by ED. So these diagonals are intersecting in this proportion of the sides. So what are the sides? AB and DC. So these diagonals must intersect in the proportion of sides as AB by DC. So these two are diagonals, these two are sides, and these diagonals are in the same proportion as that of the sides of the trapezium. So this is one more property that you must remember, and this is generally used when we are asked to calculate either the sides or the diagonals, or we can also calculate the ratio of the diagonals, ratio of the sides, anything. So all the properties that we are discussing in this video, right, these are sufficient for any exam. These are sufficient, so please remember, please recall all these properties so that you won't miss anything. The next parallelogram is kite. Let us mark this as A, B, C and D, right? And these two are diagonals. This is the longer diagonal. Let us mark it as DL, L being the larger, and BD is the shorter diagonal, right? DS, larger and smaller, DS and DL. Now in a kite, the pairs of adjacent sides are equal, right? Adjacent sides are equal. So what are the adjacent sides? BC and DC, right? So if we say BC as 15 centimeter, then DC must also be 15 centimeter. And if we say AB as 10 centimeter, AD must also be 10 centimeter because they are adjacent. So two pairs of adjacent sides, are always equal in a kite. And how can we calculate the area of a kite? Area can be calculated as, we know, half d1 d2 sine theta. That is the general formula to calculate the area of a parallelogram. But here, as the diagonals intersect, right, they bisect at 90 degrees. So half d1 d2 sine theta becomes sine 90. Sine 90 is 1. So half d1 d2, which is also known as half d1 d2 by 2. So this is the area that we use to calculate the area of the, this is the formula that we use to calculate the area of the kite. So the diagonal property is, these diagonals intersect at 90 degrees. This is 90, this is 90, everything is 90 at the intersection, at the point of intersection. So diagonals intersect at 90 degrees. Alright. And the longer diagonal bisects the shorter diagonal. It is not the vice versa. Longer diagonal bisects. Longer diagonal bisects the shorter diagonal. See this, AC is bisecting BD, so that B, this point, let us mark the intersecting point as O. BO is equal to OD, and it's not the vice versa. Shorter diagonal doesn't bisect the longer diagonal. If it had bisected, then it would have been AC is equal to, right? Sorry, AO should have been equal to OC, but this is not equal. So in a kite, remember this, in a kite, only the longer diagonal bisects the shorter diagonal. So let us look into the figures formed by joining midpoints. So in a quadrilateral, so when the midpoints of a quadrilateral are joined, right? When the midpoints of a quadrilateral, take any quadrilateral, when the midpoints of a quadrilateral are joined, right, like this, then a parallelogram is formed, right? Then a parallelogram is formed. What happens when we join the midpoints of rectangle? a rhombus is formed. You can observe, you can just draw and you can observe the you can just join the midpoints and observe the figures. And if we join the midpoints of a kite, then we will get a rectangle. We'll get a rectangle. And if we join the midpoints of a square, again we'll get a square, right? If we join the midpoint of a square, we'll get a square. And if we join the midpoints of a parallelogram, we'll get one more parallelogram. See, just observe. If we join midpoints of quadrilateral, it will be a parallelogram. If it is a parallelogram, then again we will get a parallelogram if we join the midpoints of the parallelogram. If we join the midpoints of the rhombus, then we will get a rectangle, right? If we join midpoints of a rhombus, we will get a rectangle. And if we join the midpoints of this rectangle, the inside part, again we will get a rhombus. And again, if we join the midpoints of this rhombus, we will get a rectangle, and rhombus and rectangle and rhombus and rectangle and so on. Just you can observe all this. So let us solve this. Trapezium PQRS is formed by folding triangle MRS such that vertex M lies on RS. RS is equal to root 50 and the area. Alright. So let us take PQRS is a trapezium and folding triangle MRS. Okay. So PQRS. So this is a trapezium PQR and S, right? And this is MRS. MRS is a triangle. Now this is folding. This is a folding triangle, which means if we fold this, then we will get we can get M here, M on SR, right? If we just fold this, then M will lie on SR, right? Let us draw the altitude of this triangle. So this is the altitude of the triangle MSR, and it is given that RS is equal to root 50. RS is root 50. Well, and the area of this trapezium PQRS is given as 60 square units. Alright. Now if we take the intersecting point, right, this intersecting point as O, let us say, then OM will be equal to OD, right? OM, if OM of MO is 1 unit, OD will also be 1 unit. The ratio is 1:1. Why? Because M is directly folding and it is forming at D, right? Or instead of D, we shall mark it as M1, right? So M is directly folding at M1. So the ratio of MO and OM dash will be always 1:1. And we also know that area the triangles MPR and triangle MSR, these two are similar. So we can calculate the area now. Area of triangle MPQ by area of triangle MSR. This will be equal to square of the sides. See, MPQ, the side is 1, right? The altitude is 1 unit, and the altitude of MSR is 2 units. So it is 1/2, 1:2, right? So 1:2, 1/2 square. 1/2 square. This is equal to 1/4, which means we can say that this area, this is equal to 1 unit, right? MPQ is 1 unit, whereas PQRS, this trapezium, has got 3 units, because this is 1 and this is 4. If MPQ is 1, PQRS, this trapezium will be of 3 units. But here we have the area of trapezium as 60 units, 60 square units. So 3 units is equal to 60 square units. We are asked to find the area of triangle MRS, which is of 4 units. If 3 is equal to 60, what is 4? 4 units are equal to 60 into 4/3. This is equal to 80 square units. See, why we have taken 1:1 is M is directly folding
and it is getting placed at M1. If M is directly getting placed at M1, then MO must be equal to OM. The distance between MO and OM must be MO and OM dash must be equal. So the ratio is 1:1. If this is 1:1, the altitude MO is 1, right? And the altitude M dash is 2. So the area of two similar triangles is equal to the square of the ratio of the altitudes, which is 1/2 whole square. Why we have to square is we discussed this concept in the similar triangles. If you haven't watched or if you skipped, just go through this in this video itself in the similar triangles concept. So 1/2 whole square, this is equal to 1/4, and if 3 units, if this is of 1 unit, if MPQ is 1 unit, PQRS is 3 units, and we know this PQRS is 60 square units. So if 3 units is 60 square units, what is 4 units? 4 units is equal to 80 square units. So the area of triangle MRS is equal to 80 square units. So now we entered into another important part of geometry, circles. Let's look into some basic terminology. So in a circle, let us take, this is a circle and this is the center, right? This is the center. So this is a segment, right? This is a segment. A segment can be drawn by using a chord, and let me tell you the difference between a segment, a minor segment and a major segment. Minor segment versus major segment. In a major segment, the center of the circle is included, right? For instance, AB is my minor segment. So this is my minor segment. What is the major segment? This entire thing. The remaining thing is my major segment, in which center is involved. So if center is involved, that is my major segment. If center is not involved, that is my minor segment. So as this is a chord, right? This is one more chord. This is one more chord. This is one more chord, right? These all are chords of a circle. And the longest chord is the diagonal. And what is a radian? For instance, if we take this as the radius, right, in which this radius r is equal to 1, this is r is equal to 1, and just imagine this radius instead of here, right, we have the same radius, same length on the circumference of the circle, on this circle. So this length r is equal to 1 is equal to this length r is equal to 1 unit, and this whole thing is equal to, the length is also equal to 1 unit. Now this angle is known as radian. This angle is known as radian. Why? Because here this is 1 unit, here the radius is also 1 unit. The same length is getting wrapped around the circle, So when the 3 sides are of equal length, so this is not a side, but when it is getting wrapped, so when these 3 are of equal length, the angle subtended here is known as the radian. So 1 radian is approximately equal to 57.2958 degrees. This 1 radian is approximately equal to 57.29 degrees. So we know pi radians, the value of pi radians is equal to 180 degrees, right? So these two are the things that you must remember. Now one more property that you must remember is, we know this is an arc, right? This, let me change the color. So this complete thing is an arc, right? So equal arcs subtend equal angles at the center of the circle. Let us take the same arc, the same length of the arc here. Let us assume this arc is equal to this arc. Then what happens is this angle theta will be equal to this angle. So what is the property? Equal arcs subtend equal angles at the center of circle. Alright, and we can also make it vice versa. If the
two opposite angles of the center of the circle are equal, then it must be equal arcs. Then the two angles are must be made by equal arcs. So if two arcs subtend equal angles at the center of the circle, then the two arcs are always equal. Here this arc, this yellow color, this arc is always equal to this arc. Now, is there any formula to calculate the length of the arc? This arc, is there any formula to calculate? See, what is the area of circle? Area of circle is pi r square. What is circumference of circle? Circumference is 2 pi r. So this arc is a part of the circumference of the circle. So this arc is a part of the circumference of a circle. Let us name this arc as from here to here as L, right? So this arc will be equal to theta by, this is theta, right? The arc subtends this angle. So theta by the entire degrees, the degrees of a circle is 360 into 2 pi r. So this part, this theta of this arc divided by the entire angle of this circumference will give us this length. For instance, if this is 30 degrees, so this arc, the length of this arc can be calculated as 30 by 360 into 2 pi r. Accordingly, we will substitute the values here and we will get the length of the arc. So let us look into the properties of chords. Properties of chords, you must remember this. These are important. So equal chords subtend equal angles at the center of the circle. So let us take A, B and DC. These two are the chords, right? So chord is something where the meeting point of the circle will be at 2 points exactly. So AB is a chord, DC is a chord. These are equal. AB is equal to DC. Hence the angle that is formed at the center, let us take this is theta 1 and this is theta 2. Theta 1 is always equal to theta 2 because these two angles are formed by equal chords, right? And the vice versa is also true. Equal angles subtended at the center of the circle cut off equal chords. If these angles are equal, these triangles are equal, then they must be formed by equal chords. The similar thing we observed in the arcs concept. So all the similar property. So the next property is a perpendicular line from the center of the circle to the chord bisects the chord. The perpendicular, so this is the center of the circle, right? Center of the circle. If we draw a line, and this is the chord, right? Let us name it AB. So AB is a chord, C is the center. From the center, if we draw a perpendicular bisector D, then this bisector bisects the chord. In this case, A, let us name this intersecting point as M. AM is equal to MB. Why? Because the perpendicular bisector divides the chord into two equal parts. And the vice versa is also true. A line from the center of a circle that bisects the chord is always perpendicular to the chord. So this is 90 degrees. Equal chords are equidistant from the center of the circle. Alright. So equal chords are equidistant from the center of the circle. So let us take this chord as AB and this chord as CD. So chord AB is equal to chord CD, right? Chord AB is equal to chord CD, which means from center the lengths are also equal. So O, let us take this one, this point as X and this point as Y. So OX is also equal to OY, and the vice versa is also true. They are equidistant from the center. So the next property is intersection internally. Intersecting internally. The products of the intercepts of intersecting chords are equal. Let us take this as AB, right? AB is a chord. And let us take this chord as CD and this intersecting point as X. Now, the products of intercepts of intersecting chords are equal, which means AX into XB is equal to CX into XD, right? The product is equal, always equal. And the external intersection, which is the square of the length of
the tangent from an external point is equal to the product of the intercepts of the secant passing through this point. So this is a secant, right? Let us mark this as A, this as X, this is B, and this is C. So XC is a secant. Well, secant is also a type of chord. So XC is a secant. Alright, XA is a tangent. Well, what is a tangent? The tangent is something that meets the circle at only one point. Here the point is A. Okay, so XA is a tangent, XC is a secant. Now the square of the length of the tangent, this square, which means ax square is also known as ax into ax, right? It can also be written as ax into ax. So the square of the tangent, the square of the length of the tangent is equal to the product of the intercepts of the secant passing through this point, which means bx into cx. So bx into cx. So x square is equal to bx into cx. And don't get confused, don't take bx into cb or cb into bx. To avoid this confusion, I have just rewritten the property like this: ax, bx, bx. So ending will be x, and the starting will be a, b, c, double a, and bc. So like this, you have to remember ax, right? The square of the tangent ax square is equal to cx into bx. All right, and this is one more condition of the external property of the chord. Here these two are the secants. MO is a secant, MQ is a secant, right? MO is a secant, MQ is a secant. Just ignore this part. So just look into this diagram. Here what would happen is MO square is equal to, here we can write it as OM into ON is always equal to QM into PM, right? This external point, take this as reference, take this external point as reference, and you can make it as OM into NM, which is equal to QM into PM. So this external reference must come at the end in each and every case: OM, NM, QM, PM. So this product is equal to this. So let us look into the circle properties. The angle at the center of the circle is twice the angle at the circumference subtended by the same arc. Let us take this as the center of the circle, right? Center of the circle. And if I join these two, so if I make this theta, right? So this, if I name this as theta, then the angle formed here will be 2 theta. Why? See, this is the same arc, right? This is the same arc, and this is subtending this angle as well as this angle, theta and 2 theta. So the angle at the center, which is this one, must be twice the angle at the circumference, which is subtended by the same arc, this arc. So if this is 30 degrees, this must be 60 degrees. If this is 50 degrees, right? If this is 50 degrees, this must be 100 degrees, something like that. So angle in a semicircle is always a right angle. Angle in a semicircle is always a right angle. Let us take this. This is a semicircle, right? So if we subtend any angle, let us say this angle. So this is 90 degrees. Or if we can also make like this. This is also 90 degrees. Even this is also 90 degrees, right? We can make n number of right angles. So angle in a semicircle is always a right angle. Hope this is clear. And angles standing on the same arc are equal. So let us take this chord, right? And let us take one more chord. Let us join them. So this is theta, this is theta. If you observe, these two are the angles which are on the same arc. This is the arc, and these two angles are on the same arc. So this theta, this angle will always be equal to this angle. If this is 30 degrees, this must also be 30 degrees. Alright. So the angles subtending on the same arc are always equal. These are the properties that you must remember. And the next properties are the tangents to a circle from an exterior point are equal. Tangent. Now let us construct a tangent now. So this is a circle, and for tangent we must take a point externally. So let us take this point externally and let us construct a tangent. So see, so this is my tangent, and let us mark them. The intersecting point of the tangent and the circumference of the circle. Where is that point intersecting? So this line, this line and the circle. So it is intersecting at E, and this tangent is intersecting the circle at F. So DF is my tangent and DE is one more tangent. And what is the first property of tangents? Tangents to a circle from an exterior point are always equal. For instance, if we measure these two, the lengths of these two tangents, these will always be equal. Let us measure them. DE, the length of DE is 11.4 units, and the length of DF is also 11.4 units, right? Hope this is clear to you. And two tangents form an external point subtend equal angle at the center. Let us join this D and the center. Let us join them. So let me join D and A, and also let us join EA and AF. So if we measure this angle EA and DA, this is 66 point something, and if we measure these two angles, this is again 66 point something. I think this is equal to 66.7. Yes, this is equal to 66.7 exactly. So the second property is, if we draw two tangents from an exterior point, here our exterior point is, external point is D, right? If we draw two tangents, then the angle that they form at the center of the circle are equal. This angle that is formed by this tangent is always equal to this angle that is formed by the tangent, the other tangent, DF. So let me write the properties one by one. So these are the properties of the tangents with respect to this circle. So the two tangents subtend equal angles at the center. We have 66.7, 66.7 degrees respectively. And the tangents to a circle form an exterior point, right? From an exterior point are equal. So DM, the length of DM is 11.4, has seen that, and CF is also 11.4 units. And DM and the angle formed here, this is equal to 90 degrees, right? This is perpendicular. So previously we have learned that the angle at the center of the circle is definitely twice the angle that is subtended by the same arc at the circumference. So let me show you why this is happening. So this is the same arc. C is the same arc that is subtending angle D as well as angle A. The only difference is angle D is on circumference, angle A is at the center. If we calculate, if we measure this angle, this is going to be 74.9, which means angle A must be double that of that angle, which is 149.8. If we move this, what will happen? The angle remains the same. So you can see there is no change in the measure of the angle. So this is exactly half, and if we move this, right, then accordingly the angle at the center is becoming double that of angle at the circumference. All right. What if we make it a straight line, that is 180 degrees? So exactly it is 180 degrees. So accordingly CDE, the angle at the circumference is 90 degrees. So this 90 can be anywhere. The angle that is subtended at the circumference can be anywhere. We can just play with this. However, the angle at the center doesn't change. It will be double that of angle that is subtended at the circumference. But the only condition is the arc that is subtending these two angles must be equal. Here CE is the arc that is subtending these two angles. CE is common to both of these angles. So the next concept is direct common tangents. So we have two different tangents. The first one is direct common tangent and the second one is transverse common tangents. So we shall look into the difference between these two and how we can apply these two in solving various problems. So if we take PQ, right, and RS, these two are the common tangents for the circles, for this circle and this circle, right? And the radius of the first circle, let it be R1, and the radius of second circle is R2. And if we join these two, right, let us name this line as D. Now D square will be equal to R1 minus R2. So R1 minus R2 whole square plus this CD square. So if you simplify, CD square is equal to D square minus R1 minus R2 whole square. So this CD square is also known as CD square is always equal to AB square, because we know the tangents, the length of the tangents, the common tangents is always equal. So AB square is also equal to CD square. This is equal to D square minus R1 minus R2 whole square. So this is the relation that you must remember. But how did we arrive at this? See, if we join these two, right, if we extend this line and if we join these two, right, so assume it as a straight line. All right, now this is 90 degrees, right? This is 90 degrees and 90 degree opposite side is always hypotenuse. This is hypotenuse. As this is parallel to this line, this is D and this will also be equal to D. And what is this part? Let us name this as M. So MC, what is MC? MC is my R1 minus R2. These two difference, the difference between R1 and R2 is equal to MC. So MC is equal to R1 minus R2. Alright. Now the hypotenuse square is equal to the base square into the other side square. So this is the hypotenuse square. D square is equal to the base. What is the base? R1 minus R2 whole square plus the other side, CD square. So this is how we got this. Transverse common tangents. Now again, this is the radius. R1 is the radius of this circle and R2 is the radius of this circle, right? Now if we join these two centers and if we mark it as D, now D is the distance between the centers of these two circles. Now the tangent PQ square is equal to SR square. This is one more tangent. So this will be equal to D square minus R1 plus R2 whole square. So we can prove this like that we proved previously for the direct common tangents. But this is the relation that you must keep in mind. Now alternate segment theorem. So what does it talk about? The angle between a tangent and a chord through the point of the contact is equal to the angle in the alternate segment. For instance, we have a tangent. So this is a tangent, right? And this is a tangent and the meeting point of this tangent is at B. The meeting point is B. Now the angle between this tangent and a chord. So this is a chord, right? This is a chord CB. This is B. Let me write it here. This is B. So CB is a chord. So the angle between this tangent, let us mark this tangent as ZY. Okay. So the angle between the tangent ZY and BC is this theta, right? This theta is equal to the angle between through the point of contact is equal to the angle in the alternate segment theorem. Now this is my chord, this is one more chord, AC is one more chord. This theta is equal to this, this angle is equal to this angle because this is making angle at the point of contact of this tangent and chord, and alternatively there is one more angle in the alternate segment that is also formed by one more chord. So this angle will be equal to this angle. Now it can also be like this, it can also be like this, right? It can also be like this. Now this angle will also be equal to this angle, right? It can also be like this, this angle will be equal to this angle, right? It can also be like this, where this angle is equal to this angle. So this is the alternate segment theorem. So let us solve this. In a figure given below, A, B, C are the 3 points on the circle, right? A, B and C, alright. With the center O, the chord BA is extended to a point T. BA is extended to point T such that CT becomes the tangent of the circle, okay? Tangent of the circle at point C if angle ATC, ATC is 30 degrees, ACT is 50 degrees, then the angle BOA. So BOA. The moment you see this angle, that property must remember that you must remember that property that must reflect in your mind. This angle must be double that of this. If this is theta, this must be 2 theta. But here we do not have a direct relation, so we will make it happen. Now just observe, this is 50, right? This is 50, and this is the angle made by this chord and this tangent. This is a tangent and CA is a chord, right? CT is a tangent. So at this point the angle 50 degrees is formed. So alternatively this must also be 50 degrees, right? This must also be 50 degrees. Now just observe in a macro point of view. This is C, this is B and this is T. This is a triangle, right? Already we have 30 degrees, 50 degrees and this 50 degrees. So we must calculate this. How can we calculate? The sum of all angles are 180 degrees, right, in a triangle. So this is 50, so minus 50. This is 30, minus 30. This is 50, minus 50. So the remaining angle is this one. So what is the remaining angle? This is 50 degrees. This is equal to 50 degrees. Now if this is 50, this must be 2 times of 50. So this is 100 degrees. So the measure of angle BOA is 100 degrees. And this, I think this appeared in CAT previously. Yes, this appeared in CAT. So whether it's CAT, XAT or any other non-CAT exam, first of all you must be very much clear about all the properties, and you must revise them, recollect them. And the moment you observe any figure, right, and better to practice visually rather than just mugging up all the properties. Just try to represent all the properties on a piece of paper. All right, that is the best way to finish the revision, especially during the peak moment. That is the thing that you all must practice. Let us look into the next question. The line AB is 6 meters. So this is AB. So it is given here. So AB is 6 meters. Sorry, this is not 8. This is C. So the line AB is 6 meters in length and is tangent to the inner one. So this is inner circle, this tangent. Okay, and okay, so these two are concentric circles. So what are the concentric circles? The center of any two circles, two or more circles, if the center is common, then all the circles are known as concentric circles. Yes, so it is touching at C. It is known that the radii of the two circles are integers. The radius of the outer circle is, so radii are integers. Okay, the radius of the outer circle. So we are asked to find out the radius of this outer circle. All right. Now we know that if we join these two, right, the tangent at the point of contact of the tangent with the circle, it will form a 90 degrees. So this is 90. If this is 90 and if we join these two, the angle opposite to 90 is definitely hypotenuse. We know that this is hypotenuse, this is 90, this is 90. So let us mark this as O. So AO is my hypotenuse, right? AO is my hypotenuse. And is there any measurement given? Yeah, AB is given. AB is 6 meters. AB is 6 meters. If AB is 6 meters and this is touching, this is a, the tangent is 6 meters, we're drawing this perpendicular line, which means this divides this line segment, this tangent, into two equal parts. So 3 meter and 3 meters. Now AC is 3 meters. This is 90. If this is 90, is there any triplet, right? Is there any Pythagorean triplet that we can satisfy this condition? Let us recall the Pythagorean triplets. There is only one triplet which satisfies this, which is 3, 4 and 5. Already we have 3. What is 5? 5 is the hypotenuse, which is the largest length, which has got the largest length. So this is my 5. And what is 4? The other side. This is 4. So we are asked to find out the radius of the outer circle. What is the radius of the outer circle? From here to here, which is my hypotenuse, and this is 5 meters. Is it meters or units? Okay, 5 units. And let us solve this. In a triangle ABC, the lengths of the sides AB and AC are equal to 17.5 centimeter and 9 centimeter respectively. So AB is equal to 17.5 and AC is equal to 9 centimeter. Let D be the point on the line segment BC. So let us construct a triangle so that we will understand better. So this is a triangle, right? This is a triangle A, B and C. AB is equal to 17.5 centimeter, AC is equal to 9 centimeter. Let D be the point on line segment BC, D be the point such that AD is perpendicular to BC. Okay, so AD must be perpendicular to BC, in which means it must form 90 degrees at the point of contact. So this is D. If AD is equal to 3 centimeter, so this is 3 centimeter, then what is the radius of the circle circumscribing the triangle ABC? Okay, so circumscribing, which means this circle circumscribing. All right, so circumscribe radius, circumradius, that is what we have to find out, which is denoted by R. So what is the area of triangle? There are a lot of formulae, right, in which the basic formula is half into base into height, half BH, and the one more formula to calculate the area of triangle as far as the circumradius is involved is ABC by 4R, where R is my circumradius, ABC are my sides of the triangle, right? Sides of the triangle. Let us solve this question by using only these two. Half into, what is my base? Base is, we do not know. Let us take it as BC itself. Okay, BC into, what is my height? Height is given 3 centimeter, right? Height is given 3 centimeter. So this is equal to, see, this area is obviously equal to this area, because these two are the areas of the same triangle. So this area must also be equal to this area. So this will be equal to ABC. What is A? Is 17.5, right? A is the side of AB, so which is 17.5 into what is B? B is 9, and what is C? C we do not know, that is BC, by R. What is R? The circumradius. So 4R, that is what we have to calculate. Let me rub all this. So let us strike out BC and BC, and this the R, let us move this to the other side. So R will be equal to 17.5 into 3 by 2. So 17.5 into 3 by 2, this will be equal to If you calculate, this would be equal to 26.25 units. So this is the radius of the circle circumscribing the triangle ABC. Just very simple. And this appeared in, I think this appeared in CAT. So let us move on to mensuration. It's a beautiful, easy concept. If you see, lot of aspirants are getting stumbled with mensuration. That there is nothing like that. If you understand the formula, how the formula got derived, right, to each and every 2D object and 3D object, then that is the simple formula to calculate, to revise, to apply the concepts wherever they are necessary. So let us first look into some 2D figures. The volume, the area and perimeter of the 2D figures. Volume stands for only the, applies for only the set. So circle, let us take circle. Let us take a circle. This is the center, this is the radius, right? What is the area of circle? We all know that area is pi r square. What is the perimeter? Perimeter is also known as circumference, right? Circumference of the circle is 2 pi r. Okay, so this is the area, this is the perimeter. And what is pi? Pi here is 22/7. This is equal to 3.14159 something, and it continues. And r is the radius. What is semicircle? Semicircle, let us take a semicircle. So this is the diameter and this is the radius. So for semicircle, see, for area of a circle it is pi r square by 2, but here we are considering only half of the circle. So let us divide it, pi r square by, let us take half of the area of the complete circle. And what is the perimeter? Perimeter is, see, this is my r, this is my r. So let us take r plus r, right? And this is the circumference, this is the perimeter. This is what we must calculate apart from this diameter. So what is this area? This area is pi r. Why? Because the circumference is 2 pi r for the whole circle, 2 pi r, but here we are calculating only one side, half of it. So not 2 pi r, it's only pi r. So r plus pi r, this will be equal to pi r plus 2r. This is the perimeter of the semicircle. And sector, so let me take a sector here. This is an arc, this is theta, a, b and o. This is radius. All right, so area of a sector, what is the area of this sector? Let me change the color so that it will be clearly visible to you. So this is the area that you must calculate. What is the area of the sector? Area will be given by, obviously it is subtending theta at the center. So theta by the whole angle, which is 360 degrees, right? 360 degrees into this theta of, this is O. So theta of this complete area of the circle, which is pi r square. So theta by 360 into pi r square is my area of sector. And what is the perimeter of sector? Same, theta by 360. But however, now it is not area, it is perimeter. So let us take 2 pi r plus 2r. Why 2r? Why 2r? Because this is one radius, this is one radius, r plus r is equal to 2r. And I am calculating only this area, only the area of this sector. I don't want this, I want only this. So theta by 360 of 2 pi r of the whole radius plus 2r, that part will give me the perimeter of this sector, right? Segment, let us take a segment here. So this is my center, this is my radius, this is one more radius, r, and this is the o, this is theta. Let us name them as a and b. So this is my segment. So what is the area of the segment now? What is the area of segment? This yellow colored part. See, area of segment is equal to area of this sector minus area of triangle AOB, right? Area of this complete sector minus area of triangle AOB. This gives me the colored part, which is the segment. So area of sector minus area of triangle AOB. So area of sector is equal to theta by 360 into pi r square minus what is area of triangle AOB? It's half into base into height. So this is r square into sine theta by 2. So we calculated by using here we do not know the base and height, so we calculate by using AB sine theta by 2 formula of the area calculation. So AB sine theta, what is AB? A into B, right? AB sine theta. So R and R, these are two sides, so R into sine theta by 2. So this is equal to R square into theta by 360 into pi minus sine theta by 2. So if we further simplify, we will get, so let me write the area directly. Let me write the area of the segment directly. So area of the segment is equal to r square into pi into theta by 360 minus sine theta by 2. Please remember, this theta is the included angle, this theta. Okay. And what is the perimeter? Perimeter is equal to 2r into pi into theta by 360 plus sine of theta by 2, half of theta. But how did we arrive at this formula? So if you want me to explain the derivation, I can explain you that derivation. So perimeter is something, see, perimeter of this this segment is the length of this arc, right? This arc, this length plus length of this segment AB. So this one plus this one, right? So perimeter is, what is the length of the arc? We know length of this arc is, previously we calculated, it is theta by 360 of circumference. Theta by 360 of circumference means theta by 360 of 2 pi r plus length of line segment AB. What is the length of line segment? So AB can be calculated as, see, if you draw a straight line like this, it will bisect these two equally, right? So this part is equal to this part, and theta, it is also an angular bisector, so this will be theta by 2 and this will be theta by 2. All right. So if we want to find out the length of AB, then let me take this separately. So this is the right angle triangle, and this is 90 degrees, we know. So this will be AB by 2, and this is radius, we know that, and this is theta by 2. So what is sine theta by 2? Sine theta by 2 is equal to half of AB by R, right? So for further simplify, we shall simplify 2 into R. If we just multiply both the sides with 2, r sine theta by 2, this will be equal to AB by 2 into 2. Why we multiplied? Just for the cancellation purpose. So now AB is equal to 2r sine theta by 2. So let us substitute here. AB is equal to 2r into sine theta by 2. Now this is equal to 2r into pi theta by 360 plus sine theta by 2. This is what we got here. So this is area, this is perimeter. So I'm not a person to, who actually remember all the formulae of mensuration. If you want, you can derive at the exam, because when you mug up all the formulae, the stress levels will definitely get increased, because you have to make sure that you have to remember each and everything, each and every the symbol, each and every element of the formula, which increases your stress. If you know the derivation, if you know how to derive, then you will be free. You will be like a free bird. Wherever you go, whatever the exam, you can just derive right at the moment. So just learn how to derive this and you are sorted. So cross paths. Let us find out the area of cross path, the perimeter including common perimeter, and the perimeter excluding the common perimeter. So this is the cross path, and the exterior, that is the rectangle, right? This is the rectangle, ABCD is a rectangle, and this is my path. So let us name this one as the width, right? This is the width, this distance is the width, this is the width, this is the width, and this is the width. And if we make this as the breadth, let us name it as B, and this is the length, let us name it as L. All right, so let us name this as W. So just ignore this. This is W, this is W, this is W, because all the sides are equal. Now the area of this cross path is given by this belt, right? This belt plus this belt. If you observe, this internal area, this inner area is repeating twice, right? We are calculating twice. We are calculating for the first time when we are calculating this area, and we are calculating for the second time when we are calculating this horizontal area. So what we shall do is belt 1 plus belt 2 minus the common area. We shall subtract it once. Common area. What is belt 1? Belt 1 is this is a rectangle, right? Belt is a rectangle. So this is a rectangle. So what is the area of rectangle? L into B. So what is the length and breadth? W into B, right? This is B, this is B, this is W. So length, that is B, into breadth, that is W, plus B. The same applies for this belt 2 as well. What is belt 2? This one. What is length? Length is L. What is breadth? That is W. So L into W minus the common area. This is the common area. What is this? This is a rectangle, and the area of rectangle is L into B, which is W into W, that is W square. Now this is equal to L into B minus W into W. This is the formula of the cross path, right? Cross path. Now perimeter. If you want to calculate the perimeter, you can just calculate. See, you can calculate, if you include the common perimeter, you can just calculate by 2 into L plus B. If you exclude the common perimeter, then it is 2 into L plus B, and you must exclude the 4 W's, right? This one, first one, second one, third one, and fourth one. So these 4 must be excluded, and if you are including the common perimeter, then it will be 2 times of L and 2 times of breadth. So it will be 2 into L plus B. And this is the outer pathway, in which this is the breadth, this is the breadth, this is the length, the remaining part, this is W, this is W. So each and everything is W. This is W. All right. Now how can we calculate area? Area is what is the thing that we have to calculate? The area of the inner part, this white part, right? This white part, this is the thing that we have to calculate. So to calculate the area of this white region, right, what we can do is we can just subtract the area of this bigger triangle and the area of this smaller triangle, bigger rectangle and the smaller rectangle, so that we'll get the area of this interior white part, right? So we shall subtract these two, area of outer rectangle minus area of inner rectangle. Let me erase these two. So area of outer rectangle, please remember that. What is the area of outer rectangle? It is length into breadth. What is length? Length is from here to here. Let me change the color first. So from here to here it is L, plus this extra part is there, right? This extra part is there. What is that? W and W. So what is the length of this? L plus W, right? And what is the breadth of this? What is the breadth of this? B, from here to here B. So we want this complete. So B plus this W and this W. So B plus W plus W. So what is the area of this bigger triangle? Length into breadth, which is L plus 2W. This is length. And what is breadth? B plus 2W minus. So this is the length of, this is the area of the bigger rectangle, and we have to subtract the area of the smaller rectangle. What is the area of smaller rectangle? Again, length into breadth, because this is straightforward. This is from here to here it is length, here to here this is breadth, so L into B, no more addition of width. So if we just simplify this, we'll get L plus B plus 2W into 2W. This is the area of the outer path. Just a simple calculation. And what is the perimeter? Inner perimeter. What is the inner perimeter? Inner perimeter can be calculated as 2 into L plus B, and the outer perimeter is calculated as 2 into L plus B plus 4W. See, what is the inner perimeter? This is the length, right? So L plus W plus W, plus B plus B. So L plus L, 2L, B plus B, this is 2B, so 2 into L plus B. And perimeter, outer, so this green colored part. So this is, we know, L plus W, and this is breadth, which is B plus W. So how many W's are getting added? This is 1W, this is 1W, this is 2, 3, 4, 5, 6, 7, 8. So 8 W's. 2 lengths, 2 breadths, and 8 W's. That is the perimeter of the outer pathway. And now the inner pathways. As we know, this is W, right? If we want to calculate this area, right, this interior area, please remember this, we are calculating this area. Now we know this is length, right? From here to here, this is length. We know that we shall assume that this one to be L. Now if we want to calculate this part, right, this part, this length, it will be this complete length minus this part and this part, which is W minus W. This is equal to L minus 2W. This is the length. Then what is the width? If we assume this to be B, then this part will be B minus 2W, right? So length is this, breadth is this one. So the area is length into breadth, which is equal to L plus B minus 2W into 2W. So you can just multiply this, B minus 2W into L minus 2W, and you will get. So inner perimeter can be calculated as 2 into L plus B minus 4W. Why? Because this is the length, right? L minus 2W. This is the breadth, B minus 2W. So we can add all this, L minus 2W plus B minus 2W plus L minus 2W plus B minus 2W. And if you further simplify, we will get this perimeter of the inner area, inner rectangle, inner pathway. And what about the perimeter of the outer part? Perimeter of this outer part can be calculated as, this is L, this is L, this is B, this is B. So L plus B plus B, which is 2 into L plus B. Now let us look into the 3D figures. Now let us have a look into the 3D figures. The first simple figure as far as 3D mensuration is concerned is cube. It's my cube. So let us take the side of a cube as A. This is A, this is A. So all the sides are equal. So A, this is A. Alright. Now, what is the volume of a cube? We know volume is A cube. And what is the lateral surface area of the cube? The lateral surface area, or lateral surface area, is also known as the area of walls of a cube. Please remember this. It can also be given as area of walls of a cube. So what is LSA? LSA is 4A square. So right, 4A square. So what is the lateral surface area? What is meant by lateral surface area? Only calculate the area of the faces. This is my first face, this is my second face, and this is my third face, and this is my fourth face. Ignore the top part and the bottom part. Ignore the top face and bottom face and calculate all the 4 faces, right? Now how did we get 4a square? If we take any face, that is a square, right? And what is the area of square? A square. So a square plus a square plus a square plus a square, which is equal to 4a square. Then what is the total surface area? TSA. Total surface area is, we excluded the top part and bottom part in LSA. Now we have to include, right? Everything is included in a total surface area. So this area, which is the area of the top part, which is also a square, and the area of the bottom part, this is also a square. So a square plus a square, 2 more a squares, so 4a square plus 2a square, this is equal to 6a square. And face diagonal, this is one more concept that you must have an idea. So face diagonal, what is face diagonal and body diagonal? See, face diagonal is, take any face that is the diagonal and construct a diagonal. This is my face diagonal, or this is my face diagonal, or this is my face diagonal, right? So face diagonal can be given as root 2a, right? Whereas body diagonal, what is the body diagonal? Body diagonal is the interior corner of the cube to the opposite part. Think it as a 3D, right? Just imagine the interior corner, the vertex, and the opposite corner, or this interior corner and till this opposite corner. That is the body diagonal. That is not face, that is body diagonal. So this can be written as root 3a, right? Whereas a is the side of the cube. A is the side of cube. But how did we calculate this? How did we calculate the body diagonal? Let us assume this diagonal, any of the diagonals, let us assume this diagonal to be b, right? Now b square is equal to, this is like a right angle, right? So we can apply Pythagoras theorem. B square is equal to a square plus root 2a square. Why root 2a square? This is the face diagonal. Face diagonal is also involved. So this is equal to a square plus 2a square, and this will be equal to 3a square. Now b will be equal to root 2a. You can just remember these two. Now cuboid. So what is the volume of cuboid? So this is, let us name this as breadth, this is length, and this is height. So volume is length into breadth into height. And what is the lateral surface area? Lateral surface area is also known as the area of the four walls of the room. Area of four walls of any room, of a room. This is one more terminology, alternative terminology. So LSA is equal to 2 into L plus B into H. So why did we get LBH if we in case in volume? See, volume is nothing but area of base into height, right? Area of base into height. What is area of base? This is a rectangle, right? So what is area of rectangle? L into B, and this is my height, LBH. This is how we got. And coming to LSA, area of four walls of a room. This is my first wall, this is my second, this is my third, and this is my fourth. Calculate, don't calculate the top and bottom part. So only the four faces. So the area LSA can be written as perimeter into H, perimeter into height. Perimeter into height. What is the perimeter? Perimeter of rectangle is 2 into L plus B into height. So 2 into L plus B height. This is my LSA of the cuboid. The LBH is the volume of my cuboid. And what is total surface area? Now you can calculate the top part and bottom part as well. You can include these two as well. So total surface area will be equal to 2 into LB plus BH plus LH. So we just added LSA plus the topmost part and the bottommost part, these two areas. So this is a rectangle. So area of rectangle is L into B, and the bottom part is also a rectangle, and area of rectangle is L into B. So LB plus LB, 2LB plus 2LB. If we add, you will get this TSA. So LSA plus the areas of the top part and bottom part is equal to TSA. And what is the face diagonal in this case? The face diagonal is this one. This is my face diagonal. What is the body diagonal? Body diagonal is this one, interior body diagonal. There won't be any exterior body diagonal. Body diagonal itself is interior, the concept of interior. So face diagonal can be calculated as, let us calculate face diagonal first. Face diagonal, if you observe, this is hypotenuse, right? Let us take the face diagonal here for our convenience of the calculation. So this is L, this is B, we know that. This is height, we know that. So this is like a hypotenuse, this is a hypotenuse indeed. And what is face diagonal? This hypotenuse square is equal to root over hypotenuse square is equal to L square plus B square, right? L square plus B square, and if we bring that square to the other side, it will become root. So this is the face diagonal. What is body diagonal? Body diagonal is this one, where height is also involved. So height is also involved, so it will be L square plus B square plus H square. Right circular cylinder. Now the concept of lateral surface area gets vanished, because instead of LSA it will be CSA, curved surface area, right? Because from here on there will be curved surface area. So what is the volume of right circular cylinder? Volume of right circular cylinder is pi r square h. What is the curved surface area? This is 2 pi r h. And what is the total surface area? 2 pi r into r plus h. But how did we get this volume? Volume, right? This volume, this radius, this is height. See, volume is area of the base into height. We know that. We already know that. Area of base into height. What is area of base? Area is the base is circle. As the base is circle, what is area of circle? It is pi r square, and this h, pi r square h. This is the volume. What is the curved surface area? Curved surface area is this one, the curved part. Just ignore the top face, ignore the bottom face, only consider the curved part. This curved part. Okay. So what is the CSA? CSA is the circumference of the base, right? Circumference of the base into height. What is circumference of circle? Base is like a circle. Base is a circle. So circumference of base is circumference of circle, which is 2 pi r into h. So 2 pi r h is my CSA of the right circular cylinder. But what is right about right circular cylinder? Why is this right came here? See, if you extend this, it will be a right angle. It will subtend a right angle triangle. That is why it is right circular cylinder. And TSA, total surface area. Now you can include this one and this one, these two. So total surface area is simply the curved surface area plus the top area, let's take base first. The base, area of the base, which is pi r square, and area of the top part, that is also a circle, and area is pi r square. So CSA plus 2 pi r square, which is equal to 2 pi r into r plus h. Right circular cone. What is right about this right circular cone? Right is because when you subtend this, when you draw a straight line, it will make 90 degrees, because so this is why we have this right in front of the circular cone. Alright, so volume of the right circular cone. What is the volume of the right circular cone? It is, see, volume of a cone is 1/3 of volume of cylinder, right? See, volume of cylinder is pi r square h. So volume of cone is 1/3 of pi r square h, right? Pi r square h. This is 1/3 of the volume of cylinder. What is CSA? CSA, the curved surface area. Ignore the bottom part, right? Ignore the bottom part. Just calculate this curved surface area. Here L is known as slant height. It's like hypotenuse, where L square is equal to root over, L square is equal to h square plus r square. L is equal to root over h square plus r square. L is known as slant height. L is slant height. So curved surface area is my pi r L, right? Pi r L. And total surface area, you must include the base. What is that? This part. So my CSA plus area of base is my total surface area. What is CSA? CSA is pi RL plus what is the area of base? It is like a circle, right? So what is area of circle? Pi r square. So this is equal to pi r into r plus L. Pi r into r plus L. This is my total surface area. Right triangular prism. Right triangular prism. So what is the volume of right triangular prism? It is just the area of base into height. Area of base into height. Now depending on the shape of the prism, you can see the base of the prism can also be a rectangle, right? In this case it is a triangle. So according to the shape, you must calculate the area of base. If it is rectangle, you must calculate the area of rectangle. If it is triangle in this case, so you must calculate the area of triangle as the area of base. So LSA, what is the lateral surface area? What is the lateral surface area? Is the perimeter of base into height. Perimeter of base into height. What is the total surface area? Total surface area is, you can include the two parts. So total surface area is LSA plus 2 into area of bases. The area of this part and the area of this part. So these two. So 2 into area. 2 areas. 2 into area. Right pyramid. So this is making 90 degrees. Let us assume this to be the side length of this pyramid, and this is height, and this one is slant height. So what is the volume? Volume of right pyramid? It's 1/3 of area of base into height. And what is the lateral surface area? Lateral surface area, see, just if you observe this figure, this is one triangle, this is one triangle. You will have 4 triangles, right? 4 triangles. Since it's a lateral surface area, we will ignore the bottom part since the top part is negligible now. So you can ignore the bottom part. And what is the surface area? Lateral surface area, 4 into the area of each triangular face. 4 into area of each triangle face. So 4 into, what is area of triangle? Half into length, half into base. What is base? Base is A. And what is the height? Height is the slant height, right? L. A into L. This is equal to half into 4A into slant height. So 4A is the perimeter of the base. So this is how we got the LSA, right? LSA as, let me write it here. Let me write the LSA here. So LSA is equal to half into perimeter of base into slant height. This is the LSA of right pyramid. What is total surface area? You can include the bottom, the base also. So total surface area is equal to lateral surface area plus area of base. Sphere. So what is sphere? It's a 3-dimensional figure. This is not a circle. Assume this as a sphere. Circle is 2D, sphere is 3D. So volume is 4 by 3 pi r cube. We can derive this, but I don't want to derive this now. What is you can just remember total surface area? Total surface area is 4 pi r square. Alright, this 4 pi r square is the total surface area of the sphere, and there is no lateral surface or CSE of sphere. And hemisphere, what is the volume of hemisphere? See, sphere is 4 by 3 pi r cube. Hemisphere must be half of it, because we are considering only half of the sphere. So 4 by 3 pi r cube is the volume of sphere, so hemisphere must be half of it, so it is 2 by 3 pi r cube. Since hemisphere is something like this, we are calculating the surface area too, right? Surface area, right? This surface area, we are calculating this. So surface area of a hemisphere, curved surface area of the hemisphere is 2 pi r square. Why 2 pi r square? Pi r square is the area of the circle, right? And what is the total surface area? Total surface area. Just ignore. So in CSA we ignored this top part, right? Or if you turn like this, then it will be the base. Okay, somehow we ignored this. In total surface area, just include this. So we will get CSA. TSA is equal to CSA plus area of circle. Area of circle. This is moreover like a circle. So CSA, which is the 2 pi r square plus pi r square, this is equal to 3 pi r square. This is my TSA, this is my CSA, this is my volume. Frustum of a cone. What is frustum of a cone? Take a cone, right? Take a cone, remove this part, and the remaining part that you have, that is a frustum of a cone. What is the volume of frustum of a cone? What is the volume? What is volume of cone first of all? What is volume of cone? It's 1 by 3 pi r square h. Alright. What is the curved surface area of a cone? Pi rl. Alright. So we shall use these two in order to remember frustum of a cone in a lucid manner. So volume of a cone is 1 by 3. Let me write it here. Okay, let me write the volume of frustum of a cone first. Volume of frustum of a cone is pi by 3 h into r square plus capital R into r plus capital R square. Alright, where capital R is the radius of this larger circle, that is the base. In this case it is the base, and small r is the radius of the smaller circle. Alright. What is the CSA curved surface area? It is pi into r plus r into L. L is the slant height. What is the TSA? TSA is LSA or CSA, right? LSA or CSA. So LSA plus pi into r square plus r square. Please remember this small r, capital R, right? Okay, so how can we remember this? We shall just compare these two with the volume of cone. Volume of cone. What is volume of cone? Let me change the color first. Volume of cone is 1 by 3 pi r square h, right? So 1 by 3 pi h, everything is same. 1 by 3 pi h, 1 by 3 pi h, everything is same. Now instead of r square, we have r square plus small r square plus capital R square plus small r into capital R. This is how you remember. Everything is same, but instead of r square, we have small r square, and we have capital R square, and we have one small r and one capital R, the product of these two. What is CSA of a cone? CSA of a cone is pi r L. Here pi and L are same. The only one that is getting us into trouble is small r. So instead of small r, we have capital R plus small r. Alright, and TS is LSA plus pi into r square plus r square, capital R square plus small r square. This is how you remember. And let us solve this. A ball of diameter 4 centimeters is kept on top of a hollow cylinder standing vertically. Alright, the height of the cylinder is 3 centimeter, while its volume is 9 pi centimeter cubic centimeter. Yes, then the vertical distance in centimeter of the topmost point of the ball from the base of the cylinder. Alright, so cylinder is given, so let us form a cylinder. So this is my cylinder. Alright, so a ball of diameter 4 centimeter. So ball in the sense is a 3D. So let us take, it will be in the shape of a sphere. It will be in a shape of sphere. Right. So this is the ball of diameter 4 centimeter. So let us assume the center to be here, and if we join this to, this is my radius, right? This is my radius, and if the diameter is 4 centimeter, radius is 2 centimeter. Radius is 2 centimeter, and this is the center of the cylinder, right? Center of the cylinder, and if we join these two, we'll get a right angle triangle. This is 90 degrees, right angle triangle. So here we know the height of the cylinder. Height is 3 centimeter. So let us take this height is 3 centimeter, and the volume of cylinder is given 9 pi centimeter cube. So what is volume of cylinder? It is pi r square h, right? Pi r square h, and this is equal to 9 pi. And we know the height is 3 centimeter. So pi r square into 3, this is equal to 9 pi. Let us cancel pi and pi, 3 and 3. So r will be equal to root 3. Radius is equal to root 3. So this radius from here to here, this is equal to root 3. This is equal to 2. And let us calculate this part. So 2 square is equal to h square plus root 3 whole square. Now 4 is equal to h square plus 3, and h is equal to 1. So h is equal to 1. This is root 3 and the hypotenuse is 2. Now if you observe, the diameter of the ball is 4 centimeter and the radius of our cylinder is root 3. So which one is bigger? Obviously ball is bigger than the cylinder, the base, the topmost part of the cylinder. So do you think the ball fits exactly on the topmost part of the cylinder? No, it won't fit. So definitely the sphere will have the center not exactly here, it will have the center here, which means this is our cylinder, right? If this is our cylinder, the sphere will be somewhere like here. So this will be the center. Okay. Now if this radius, this is 2, this radius is 2, from here to here this will be one more 2, this is also radius. But what are we asked? We are asked to calculate the vertical distance from the topmost point to the ball to the base of the cylinder. So from here till here we are asked to calculate the vertical distance. From here to here we know it is 3 centimeter. From here to here we know it is 1 unit for 1 centimeter. From here to here we know it is 2. So 2 plus 1 plus 3, this is equal to 6. 6 is our answer. 6 centimeters. So we have covered all the concepts that are important for CAT and for all the non-CAT exams. No, nothing is exceptional. So kindly revise each and every concept. If you can recall all these concepts, then you can attempt any question. It can be any question, it can be any difficult level. You can use these concepts and get answers for any question. So kindly remember and revise this. If you haven't subscribed our channel, do subscribe it for more updates. Thank you and all the very best.